Okay, perfect. No, in the sense I don't have to take care of this part. That's what I meant.
He will come here, but with 5 minutes of delay, maybe.
Okay, I will. Good morning, everyone. I think we should start. I'm Federico Lelli, and I will be the chair of this session. I have two little announcements. The first one is that we will take a picture at 12 at the end of this session in this room, so please stay, don't go away if you want to be in the picture. And the second one is please check the Slacks because some discussions will continue there. There is not a lot of time for questions, so if I cut you out in the question, please write that on Slack. So the first speaker is actually going to be online, is Viviana Gamaldi. It's an invited talk about dark matter searches in dwarf irregular galaxies with gamma ray observatories. So let's hope that the Zoom works.
Hi, Francesco, can you hear me?
Yes, we can hear you. Would you like me to give you a 5-minute warning, but I will have to interrupt you?
Okay.
Or otherwise you can take care of your time as you prefer.
I mean, you can give me the warning as you prefer.
Okay, I will just, at some point, I will say 5 minutes.
Okay, great, thanks.
Please start, thank you.
I'm going to share the screen, so please let me know if this is working. I think so. I think I see my slide in the screen, yeah. Okay, so. Okay, so first of all, I would like to thank the organizer for this kind invitation, and I really regret that I'm not able to be here in presence, but
Viviana, we can see the slides, but they're not full screen. I don't know if you prefer to put them full screen.
Is this better?
Yes, now we can see them full screen. Thank you.
Okay. Okay, so my talk today is about dark matter searches in dwarf irregular galaxies. And sorry, this is the outlook of my talk. So first of all, I would like to introduce indirect detection of dark matter, just people that are not very expert in this field. And then I will speak about dwarf irregular galaxies as new target for dark matter indirect searches. After, I will give you the state of the art of the indirect searches of dark matter with several instruments, in particular gamma ray instruments. And then I will give you some observational prospects that about the constraints that we hope to get on the dark matter parameter space with the next CTA. So very generally speaking, everybody knows that we have several dark matter hints in the universe at all scales. In particular, at galactic scales and local volume scales, we have the observation of rotation curves that say us that we have dark matter in this object in spiral galaxies, such as in duospheroidal galaxies. And the presence of this matter is given by the study of the motion of the rotation curve and dispersion motion of this object. At the level of galaxy cluster scale, we have other mass traces like gravitational gansing and the traces of gas distribution in clusters that also give us the information that some dark matter exists in the universe. And finally, on cosmological scales, we have the study of the cosmic microwave background anisotropies that again say us that a dark matter component exists in the universe. And in particular, in this case, we are able to determine the percentage of the abundance of dark matter that is around the 27% of the total content of the universe. So, what about indirect searches of dark matter? In this case, we are assuming that the dark matter is a weakly interactive massive particles, indeed a WIMP. And with this hypothesis, we can assume that the dark matter exists in the halos, in dark matter halo of astrophysical objects. And these particles can annihilate or decay and produce standard model particles, which again hadronize or decay to produce secondary particles such as neutrinos, gamma rays, proton, antiprotons, and so on. So this is the main equation for dark matter indirect detection. This is made of astrophysical factor terms that includes the distribution, the hypothesis on the distribution, and indeed give us an idea of the dark matter content in the astrophysical object that we decide to analyze. And then we have this particle physics part that give us an intuition of the flux of secondary particles that we should expect in the astrophysical object due to the annihilation of dark matter. So about gamma ray telescope, we have a lot of gamma ray telescope that allow us to make indirect searches for dark matter. In this talk, I will speak about these 4 telescopes. The first one in the Large Area Telescope of the NASA. It is a satellite. And then we have 3 ground-based telescopes like HESS telescope, the Hawke telescope, and the next CTA. Now I would like to introduce the different astrophysical targets that we can use to make indirect searches of dark matter. So the first one, as I told you before, are spiral galaxies, of which we can determine the rotational curve, but also in particular the duospheroidal galaxies that are satellites included, embedded in the halo of big spiral galaxies. Also, I told you galaxy clusters are good targets for dark matter searches, and these are considered like the benchmark ones. The bigger reason to make these targets benchmark target for dark matter searches is mainly the dark matter content of this object that is dominant with respect to the baryonic content, and indeed, as a consequence, the astrophysical background that is negligible mainly in duospheroidal galaxy, while in galaxy cluster not to be modelized. So dwarf irregular galaxies are indeed considered as new target for dark matter searches because till few years ago, they was not considered for this kind of searches. In this proof of concept paper, with Caterina Carocas and Paolo Salucci, we proposed this target as a new target for dark matter indirect searches. And in the next slide, I will indeed to show you why we claim this in the proof of concept paper. In order to do so, I will compare dwarf irregular galaxies with dwarf spheroidal galaxies, and this is because dwarf spheroidal galaxies give us so far the most stringent constraints on the dark matter parameter space. So, as I just tell you, dwarf spheroidal galaxies are satellite of the Milky Way, so they are basically sub-halos of the Milky Way halo. They are pressure supported objects, and indeed their kinematics is very different from the kinematics that we find in dwarf irregular galaxies. In fact, dwarf irregular galaxies are not satellite of the Milky Way. They are independent galaxies in the local volume, and they are rotationally supported objects. Indeed, for this galaxy, we have a rotation curve. So, because of these characteristics, one of the main differences between these two kinds of objects is the distance. So, dwarf spheroidal galaxies are closer to us with respect to dwarf irregular galaxies. But on the other side, dwarf spheroidal galaxies are smaller objects in terms of mass with respect to dwarf irregular galaxies. When we consider both these factors, at the end, we get that the J factor, the astrophysical factor that give us the intuition of the dark matter content in the astrophysical object is basically comparable both for dwarf spheroidal and dwarf irregular galaxies. And moreover, we will see that when we take in account also the substructure in the two different objects, in the case of dwarf irregular galaxies, we get a Niger boost with respect to the one that we can get on dwarf spheroidal galaxies. And this is for the same nature of the object themselves. So finally, about the astrophysical background, as I told you, dwarf spheroidal galaxies are considered very good candidates for dark matter indirect searches because they are made of all star population, and this means that the astrophysical background in gamma rays is negligible with respect to the emission in gamma rays that we expect from dark matter annihilation event. In the case of dwarf irregular galaxies, instead, we have a star-forming region made of young stars, and indeed we expect an astrophysical background in gamma rays. But what we show in this proof of concept paper is that basically due to the morphology itself of the galaxies, this gamma ray emission from the astrophysical distribution is negligible, because basically these dwarf irregular galaxies are made of a very small star-forming region in the middle of the halo, and then a huge dark matter halos. This is the main reason that makes the astrophysical background in dwarf irregular galaxies negligible, as well as in dwarf spheroidal galaxies. So in this slide, you have like a quantification in some sense of what I just claimed. So in the left side plot, that is this one, you have an emission of a sample of dwarf irregular galaxy actually in general. And in particular, there is the infrared luminosity and the gamma ray luminosity for a sample of different objects. So our dwarf irregular galaxies are included in this range of mass, and this is why they are not detected in gamma rays as astrophysical objects. So bigger objects like the Large Magellanic Cloud or the Small Magellanic Cloud are in fact detected in gamma rays by Fermilab. And on the right side plot, what you have again is an estimation of the gamma ray emission that we expect in these galaxies. The magenta point are the astrophysical gamma ray emission, while yellow, blue, and green point give us an estimation of the gamma ray flux that we expect from dark matter recognition event for different dark matter masses. These points are calculated for an initial sample of 30 galaxies. And you can see here that all these fluxes are estimated to be lower than the Fermi-Lat detection threshold. So this is in agreement with the fact that these galaxies are not detected in gamma rays. So of this initial sample of galaxies, we select a smaller sample of objects with the best J factor. So this taking account the dark matter content and the distance of these galaxies. And you can see in this plot that this J factor are comparable with the J factor of some duospheroidal galaxies. And you have that few objects actually have a higher J factor within the full sample. And also that the angular extension of this object is actually high. So these objects are not point-like objects as duospheroidal galaxies. So one other important point for these galaxies is indeed the study of the rotational curve. And this is because these objects are a laboratory for the Caucas problem. So in this plot here, you have the rotational curve of the IC10 galaxies. So these are the data of the rotation curve, and the blue full line is a fit of this data with a bucket core profile. Actually, the best fit of this data is given by this core profile. What happened here is that when we try to fit this data with a Navarro-Franken-White in the CAS profile, we are not able to get the parameters that are in agreement with the cosmological standard model and indeed the cosmological simulation. So what we did here was to assume that the total mass of the galaxy is the one given by the fit of the core profile, and starting from this mass, we construct the parameters of the Navarro-Franken-White profile in agreement with the cosmological standard model. This means that this dashed line is not a fit of the data, but it is a theoretical model constructed starting from the Alouette cosmology in some sense. And finally, we took into account the boost due to subtraction in both cases, in both models. So just a quick reminder, substructure are basically the effect of the evolution of dark matter. So we have subplants in a dark matter halo, while the density of the dark matter is higher than in the mean halo. So this substructure has been studied and simulated, and we assume indeed 3 different models. The one is the bucket profile without any kind of subtraction, that is called mean. Then we have a medium model that is the core profile with the minimum value of substructure, and then we apply the maximum value of substructure to both bucket and Navarro-Franken-White profile. And this way we can get a boost on the initial calculated J factor, astrophysical factor of up to 5. So we model this dark matter distribution with Campi, that is this code to compute gamma ray signal for dark matter structures. And indeed, this is the minimal model, indeed the bucket profile without any substructure for IC10. This is the medium model for the bucket profile, and this is the maximum model applied to both the bucket profile and the Navarro-Franken-White. Finally, we use this dark matter modeling to make the analysis of the Fermi-Lat data. We analyzed 11 years of LAT data. We perform indeed an extended analysis, and as usual,
5 minutes left.
Okay, As usual, we consider 3 different annihilation channels. We don't have any significant emission detected, and indeed, we can set constraints on the dark matter parameter space. That is this one. We have an annihilation cross-section and the dark matter mass, and these are the constraints that we get on this parameter space with the Fermi-Lat analysis. This is the blue line. So this extended analysis in agreement with the first proof of concept paper, that is this dotted yellow line, where the analysis is performed as point-like. And we can see that our constraint 4 or 5 away from the thermal annihilation magnitude, more or less far away from the most stringent constraints that we get on this parameter space from dwarf spheroidal galaxy. That is this green dotted dashed line. So this bump here is probably given by a mismodeling of the galactic foreground. So I will go quickly through the other instruments. This is the limit, the constraints that has been obtained by the S collaboration. They use a different modelization of the dark matter modeling with the core Navarro Franken-White. And basically, we can see that they are far away from the thermal annihilation cross-section, but this is also due to the fact that they analyze higher energy. So it's kind of included in this kind of analysis. What about OAK? The OAK collaboration analyzed the first 30 full sample of 30 galaxies. This is distribution of the galaxy in the OAK sky. And they use the same dark matter modelization as in the first proof of concept paper. And they show here the limit. This is the combining limit, that is the blue line. They show this limit compared with this dotted line, that is the constraints that we get with Fermi-Lat, and also with the Hess instrument, that is the dashed orange line. And here the interesting fact is that the best target is different from the one that we get with Fermi-Lat, for example, and this is probably due to position of the instrument, modelization of background, I mean, probably internal stuff. So this is an overview of the state of art of the searches with dark matter in dwarf irregular galaxies with these 3 instruments, Fermi-Lat, Hess, and OAK. And to conclude, I would like to give you these preliminary results that we get analyzing as a projection of the results that we hope to get with CTA by analyzing dwarf irregular galaxy. So in this plot, we use for this analysis the same dark matter modeling that we used before for the Fermi-Lat analysis. As an addition, we take in account the astrophysical emission internal of each object. So here you can see that the blue line, the light blue line is the limits that we get with Fermi-Lat. The dashed pink line is Hess, the dotted red is OAK, and you can see here that the black blue line are the limit that we expect to get to CTA. So this is very interesting because we hope to get the most stringent results up to 100 GDP with the next observation of this object with the CTA. So I'm going to the conclusion of my talk. So I think that we can see that the dwarf irregular galaxies are now comproved target of interest for dark matter indirect detection. They have been they can include the substructure model, enhance the J factor up a factor to 5. We get the first extended analysis of dwarf irregular galaxies with Fermi-Lat with 11 years of that analysis. And we get interesting results because also if we are not able to get constraints that are more stringent of the spheroidal galaxy, we are not far away from the thermal annihilation cross-section and from the constraints that obtained so far. So also CTA will improve the current available constraints for higher energy scales. And in general, independently from the instrument that we use, it will be very important to get a complete and better understanding of the kinematics of this object in order to make these constraints more robust. And also, we hope that probably there some more interesting objects can be discovered in the future with big halo and probably an astrophysical emission so small that has not been discovered so far. So thank you for your attention.
Thank you, Viviana. Are there questions? Don't be shy. Yes, Jonathan?
So I have a question. So in your modeling, you assume that the halo mass of the Chord-Burkhardt profile is the same as the NFW. And so I was wondering why you assume this, because I feel it's quite a strong assumption for the comparison.
I mean, the point is that so when you feed the data of the rotation curve with the Navarro-Franken-White profile, you directly obtain some parameters that are not in agreement with the cosmological standard model and cosmological simulation that tell us that the dark matter distribution galaxy is generally a Navarro-Franken-White light profile. So this is something very strong because tell you that something is not happening as you expect. In order to get something that could be in agreement with the cosmological standard model and simulation, the only thing that we can do is to make some assumption. So we decide to assume that the estimation of the dark matter mass in this object is right, but probably the distribution, the spatial distribution, is different from the one that we could get by a direct fit of the data. And this plot is actually to show you that this will be the rotation curve that we could get when we construct the Navarro-Franken-White theoretically. Now, this is an assumption, of course, and you can see from here that also because the data are taken from the very inner part of the galaxy. Of course, you have some agreement in this region, but then you have some distances here from the Navarro-Franken-White model and the bucket profile. So actually what this is telling you is probably that the cosmological simulation don't work very well for this kind of object, and we should improve our modelization of the baryonic effect in the dark matter halo in order to get some prediction that are more in agreement with the data.
So we have time for one or two short questions. There was Gauri first.
Thank you, Viviana. I'm Gauri. Okay, thanks for introducing me already. So I wonder that if we could do this same study with dwarf galaxies with upcoming telescope, do you have any idea? Can we go to the dwarf galaxy regime? Because here you are dwarf irregular galaxies. Probably you are looking very dark matter dominated systems, right?
I'm not sure if I got the questions, but so maybe it's better if you repeat the question, sorry.
So can we do the similar study with dwarf galaxies with upcoming telescopes like CTA? Can we constrain these inner region with CTA?
I mean, the inner reason, I mean, the kind of instruments are different. So the inner reason, you mean the rotation curve?
Yeah. Means from CTA observation, yeah.
Yes,
Yeah.
I mean, the problem is that, okay, from CTA is not an instrument that give you the possibility to study the rotation curve. The rotation curve are studied with the survey, as you test, actually in infrared or visible, where you can see these galaxies, because these galaxies are actually visible as infrared emission. And from there, you get the rotation curve of the galaxies. Then with CTA, what you are trying to get is a gamma ray emission of these galaxies. And there, what happened is also that the angular resolution of the instrument is lower with respect with infrared instrument, for example. So from there, you can just get an integrated emission of, if you want, in gamma rays, and compare this with the one that you expect for the dark matter annihilation. And the other point is about the astrophysical emission itself in the galaxies, because here, for example, I show you the background, the astrophysical emission, indeed, the background that we expect for the Fermi-Lat energy range. When you go to CTA, this energy range change. So also this the expected astrophysical emission change. So you have to weight in some way all this effect. And I think that because, I mean, the rate also, I couldn't show too much information here because that's a paper collaboration, CTA paper collaboration. But also the ratio between the astrophysical emission and the dark matter flux that to expect in some sense change. And this is probably also one of the reasons, because at the end, when you get taking account this astrophysical emission, you get like more stringent constraints.
So I'm afraid we don't have time for other questions, but please ask them on Slack so the conversation can continue. Let's thank Viviana again for her talk.
Thank you.
The next speaker is Carlo Nipoti, who will tell us about dwarf spheroidal galaxies as dark matter laboratories.
Thank you, Federico. Good morning, everybody. And first of all, I'd like to thank the organizers for giving me time to present my work. So I'm going to talk about dark matter, in particular in dwarf spheroidal galaxies. We have just heard in this previous talk about how important it is to measure dark matter distribution in dwarf galaxies for indirect dark matter detections. Also, it's very interesting, as we have seen in the first day of the meeting, for our understanding of galaxy formation on the small scales. And I'm going to present work done by our group in Bologna in collaboration also with the Oxford group and the group in Tenerife, and in particular about 3 dwarf spheroidal galaxies, which you see here highlighted in this map of the dwarf galaxies around the local group. In particular, the Fornax dwarf spheroidal, the Sculptor dwarf spheroidal, and Leo 1 dwarf spheroidal. So I'm going now to focus on dynamical modeling of dwarf spheroidal galaxies. And if you want to constrain the dark matter distribution in these galaxies from a dynamical point of view, what you'd like to do is, first of all, to verify that the system is close to equilibrium, so that you can build a stationary model for the isolated system, even though these are satellite galaxies. And so to assess the importance of present-day tidal effects on the dwarf. And this is something you can do running M-body simulation of the dwarf orbiting the Milky Way, especially using up-to-date observationally motivated orbits that we now have thanks to proper motions measurements and radial velocity measurements. And then if your assumption of stationarity for the galaxy is good enough, you can go through a stationary dynamical model. And in particular, the approach we have used is using time-independent distribution functions and then comparing these models with the kinematics data on a star-by-star basis, so exploiting all the velocity distribution of the stars in the galaxy. So let's start from the Fornax dwarf spheroidal. First of all, we have run and body simulation of the Fornax dwarf orbiting the Milky Way, and considering this observationally motivated orbit, recent constraints also on the orbital parameters of the dwarf. And then you follow the evolution with the n-body simulation of the galaxy in the potential of the Milky Way, and you can assess the importance of the tidal effect. And the bottom line here is that the present-day tidal effects on Fornax are small, so it's reasonable to make a stationary isolated dynamical model of the galaxy, even though over time the dark matter fraction lost can be important. This is not affecting much the central parts in which you have stars. And so in this work led by Raffaele Pascale in Bologna, we applied these models based on distribution function that depends on the action integrals on the data of the dwarf spheroid or the Fornax dwarf spheroidal galaxy, and I mean, the result of the analysis in which, as you see here, we reproduce the line of sight velocity distribution at different distance from the center of the galaxy for the stars of Fornax. And finally, you get a good measurement of the dark matter density distribution here, and also the anisotropy distribution of the galaxy. These are quite flexible models. And so in the end, what we get for this galaxy is that the dark matter distribution has a wide central core in the density profile, about 1 kiloparsec core. And as you see here, the density distribution compared with the other works, there are, I mean, different results in the literature, but we find quite robustly that you have a core in this galaxy. And it is important to stress that this is what we would call a non-dominant halo, in the sense that the mass ratio, dynamical to luminosity ratio within the half-mass radius of the star for this galaxy is about 7. So for dwarf spheroidal galaxy, this means that stars are important, and we get a big core in the dark matter density distribution. Let's move to the Sculptor dwarf spheroidal. And again, we did the same approach. First of all, we ran n-body simulation following the evolution of the galaxy model in the tidal field of the Milky Way over observationally motivated orbits. And I mean, also here, the bottom line is that also for Sculptor, the present day tidal effects are small, so it's reasonable to consider a stationary model for this galaxy and compare equilibrium models with kinematic data. And in this case, I mean, we used recent spectroscopic observational data by Tolstoy et al. And again, compare this data with distribution function-based models. And in particular, we build now models in which we have, beside the dark matter halo, 2 different distribution functions for 2 stellar populations, the metal poor and metal rich stellar population of Sculptor. As you see, the more concentrated here, metal rich population, and the more extended metal poor population. And here you see a comparison between the data also for the velocity dispersion of the 2 populations. So at the dark matter density profile, you see here again, our result is the black line here in comparison with other previous result in the literature. What we find is that in this case, you have a mild cusp density distribution for the dark matter halo. Finally, the third system I'm going to talk about is the Leo-1 dwarf spheroidal. This is the most distant dwarf spheroidal that is a satellite of the Milky Way. And in this case, we actually didn't explore with n-body simulation the tidal effects. But as you see from this diagram here, the present day distance from the center of the Milky Way is around 260 kiloparsecs. So you're reasonable to expect that the present day tidal effects are small, even though in the past the pericenter could have been small. And again, similar kind of dynamical models. In this case, we consider a stellar distribution, a dark matter distribution with distribution functions, plus we added the possibility to have a central black hole in the mass distribution of the system. And again, here you can see the results of the fitting to the surface brightness profile of the galaxy and examples of fitting of the line of sight velocity distribution of the stars. And the reason why we included also the possibility to have a central black hole in the model is that there has been recently a claim of a detection of a black hole of the mass about 3×10⁶ solar masses in this galaxy, in this dwarf galaxy, which has a similar stellar mass, which is about 6×10⁶ stellar masses. In fact, the result of our analysis is kind of different in the sense that we put an upper limit to the black hole mass, which is 7×10⁵ solar masses. And we are marginally consistent with the result of Bustamante-Rosell, but we tend to exclude the hypothesis that you have a supermassive black hole in this dwarf galaxy. Thank you. Sorry. This was for the chair, but thank you anyway. You still have to look at a few slides. So what about the dark matter distribution in the Leo 1 galaxy? Again, here we are in a regime in which the halo is not dominant, factor M over L about 8. And as you see here, what you get is a dark matter distribution with a small core, around 100 parsec core in the center. And here you see also comparison with few previous results with, I mean, do not go to the very inner part of the density distribution. So overall, from the point of view of galaxy, our understanding of galaxy formation for the dwarf scales, what we get, consistent also with previous results, as you see from this plotting in which we have dynamical mass as a function of luminosity for the dwarf galaxies of the local group. Here are the galaxies we studied. What you get is that M over L in this plot is increasing in this direction. And what you get, the trend is that you have Caspi halo when your M over L is high, and your core halo when your M over L is small, like in the Fornax or the Leo 1 case. And if you are able to constrain the dark matter distribution, you get interesting information also for dark matter particle models. And in particular, we were able to, as you see here, to estimate accurate J factor and decay D factor profiles for annihilation and decay of dark matter particles for our galaxies as a function of the angle over which you see your galaxy. And also you can have a good estimate of what is called the ρ 150, that is the central dark matter density measured at a distance of 150 parsec from the center. Here is you see other estimates for the galaxies compared to other results in the literature. And this is particularly interesting for models of self-interacting dark matter, which for which this kind of measurement combined with the pericentric radius of the orbit is an important constraint. And as you see from this plot here, there is also an empirical anti-correlation between this central dark matter density and this pericentric radius of the dwarf galaxy. So here are my conclusions. So just very briefly, we have this interesting upper limit for the Leo 1 spheroidal central black hole mass. And overall, by accurately measuring the dark matter distribution, you get Caspian halo for the higher M over L, and you're able to measure JD factors and the central dark matter density. Thank you very much.
Questions?
Thank you for the talk. I have a question. When you were modeling metal poor and metal rich population in, I think, the first case, based on the model you got, what can you say about formation scenarios of this subhalo?
Well, I'm not sure how to come back with this slide. So, okay. This is something, I mean, you information about formation scenario just, I think, comes from the distribution of your populations, so that you have a more concentrated metal-rich population and more extended metal-rich population, even though you don't go through dynamical models. And for this to be the case, there are different possible scenarios, like you have a first population that is forming, and then the dynamical evolution of the system is bringing this population to be more extended, and then a second burst of star formation is more central, or also different kind of hypotheses like merging or different things.
We have time for one last question, and if the next speaker can already start coming over, Pavel.
Yeah, thank you for the great talk. I think you deserved a double round of applauses. If I read correctly the plots, I saw that the typical size of the dark matter core that you are finding is typically one effective radius. I was wondering if I read it correctly, and if this is a constraint in the model, or it really just comes out naturally to be the core of the size equal to one effective radius.
Sorry, the question is whether you expect it or
yeah, like
it's not something that is, the dynamical model is completely free to have even no core or whatever.
Okay.
So this is something that is the end product of your dynamical analysis, and the reason that is not far from the effective radius of the galaxy must be more related to evolution and formation of the galaxy itself, and this. We expect that is where the baryons are important, that you can have important effects on the dark matter distribution, and this is where you have the bulk in the end of the stars of your distribution.
Thank you.
Thank you.
Okay, let's thank Carlo again. The next speaker is Nancy Patel, talking about probing dark matter with weak and strong gravitational lensing mass models. Let's wait for the presentation to be uploaded. Is it? Oh, it's there. All right, okay. Please.
Hello, everyone. First of all, I would like to thank the organizers for giving me the opportunity to present here. So I'm a PhD student at Durham University, and I'm going to talk about probing dark matter with strong and weak gravitational lensing mass models in galaxy clusters, particularly Abel 2744. So in the coming slides, you will see what galaxy clusters are and how we can use gravitational lensing in galaxy clusters, and the survey that I use called the Buffalo survey, and I'll present the mass model methods that I'm using. So to get some motivation, although everyone knows about it, the term dark matter was first coined by Zwicky in 1930s while he was studying coma cluster, but not until 1970s that it was confirmed that the mass budget of the universe is dominated by dark matter, and until these days, we do not know what it is. So one of the best places to study dark matter are these massive structures called galaxy clusters. So they are the largest gravitationally bound objects in the universe, and they're composed of a lot of dark matter, very hot X-ray emitting intra-cluster medium, and hundreds to thousands of galaxies. So we can study these galaxies using optical wavelength. We can use X-rays to study the hot intracluster gas, but we need a more indirect way to study the dark matter in cluster. So we use something called gravitational lensing, and Gravitational lensing is basically the deflection of light coming from a background object due to intervening mass of object. And as a result of this deflection of light, we see distorted, magnified, and sometimes also multiple images of the same background sources, as you can see in the image there. So the light coming from the galaxy is deflected by the galaxy cluster, and as a result, we see two images of the same background source in the cluster plane. So we can mainly divide lensing into two parts. So in the core of the cluster, where the density is very high, we observe strong lensing, and there are it is marked by very large distortions and multiple images. So just to note here, the positions of these multiple images acts as the constraints in the strong lensing region. But as we go further away in the outskirts of the cluster, where the density is very low, we observe weak lensing. And the distortions here, unlike strong lensing, are very, very minor. And we need more statistical ways to measure the weak lensing signal. And the shapes, the distortions in the shapes of the background sources here acts as the constraints. So galaxy clusters are very, very massive, and as a result, they act as a very powerful lens. We can do many things with clusters lenses, and one of the things that I'm interested in is mapping the dark matter distribution inside the cluster. So example is the IAU 370, which you can see. So there are X-rays in pink color and lensing maps seen in blue color, and we can clearly see the difference between where the gas is and where the prediction is from the lensing maps. So apart from having the mapping the matter distribution inside the clusters, we can also use cluster lenses to study background objects, as well as to understand the geometry of the universe. But in order to do all this cool stuff, we need massive clusters. And I'm using the Beyond Ultra Deep Frontier Field and Legacy Observation Survey, the Buffalo Survey, which is based on the 6 Hubble Frontier Field clusters. And in addition to the Hubble Frontier Field data, it has the extended wings, as you can see here shown in pink color. And two main goals of the survey is to study dark matter using strong and weak lensing. So by making very high precision mass model of galaxy clusters and using these mass models to detect and study substructures. And another goal of the survey is to study the distinct universe, because as I mentioned earlier, we can see the high redshift galaxies and sources because of lensing effects. And I'm particularly interested in a cluster called IAU 2744, which you can see here. It's a very, very massive cluster, and I'll talk about it in a few minutes. So before going on to IAU 2744, I would like to present the methods that I'm using. So in the core of the cluster, where the density is high, we do strong lensing, and we parameterize the mass decomposition. We divide the mass into two components: the large scale structures, or the large scale component, which is the cluster scale halo, and the small scale component, which is basically the cluster galaxies, which you can see here in cyan colors and the orange color. And we parameterize our mass distribution using a density profile. And here I'm using the DPI, which is the dual pseudo-isothermal elliptical mass distribution profile. And to constrain our mass model, we need our constraints. So as mentioned earlier, in the strong lensing region, the positions of the multiple images acts as the constraints. So here's the constraint. For example, this arcs that you see here is the same background image, and we take these multiple images as the constraints. And now we need to optimize our mass model in the strong lensing region, for which we use a software called LensTool. And then we move further away in the cluster in the weak lensing region. So opposite to strong lensing region here, we are using a more non-parametric, flexible grid of mass pixels. And we distribute our mass models into this a non-uniform grid made up of made on the smoothed light map of the galaxy cluster. And again, we define it through a density profile. And here we're using the truncated dpi, which is basically the circular version of the dpi profile that we're using in the strong lensing region. And for the constraints here, as mentioned earlier, the shapes of the background sources are the constraints. So we need to collect all the background galaxies and make a catalog and use them as a constraints. And again, we use lens tool to optimize our mass distribution in the weak lensing region. So now I'm moving further and talking about Able 2744. So Able 2744 is a massive cluster at a redshift of 0.3. And there are lots of activities going on inside the cluster. For example, you can see there is 2 BCGs in the core of the cluster, and there are also some other activities, mergers going on in the cluster. So just so that there is no confusion, in the next coming slides, all the strong lensing features will be marked by yellow color and all the weak lensing by the magenta color. So talking about strong lensing first, in the core of the cluster, as a constraint, we only take the spectroscopically confirmed multiple images, which are the constraints here. For these clusters, we have quite a few multiple images, so it's going to give a very precise model in the core of the cluster. And we need to decompose our mass distribution. So we need the small scale components, which are the galaxies inside the cluster. And it has been seen that the galaxy cluster have this very old red and elliptical galaxies called the red sequence. And it shows a trend in the color magnitude diagram, as you can see here, which are very red and these ones. So we take all these galaxies as the cluster galaxies, and we also have these spec-Zs for some of them, which are shown by the crosses there. So now that we have our mass decomposition constraints, we can optimize it using lens tool again. And we move further on to the weak lensing part. So for the weak lensing, we need the background sources, we need the background galaxies, and we need to make sure that we do not contaminate our galaxy catalog by any kind of cluster galaxies or foreground galaxies. So here we use the color diagram, as you can see here. So I'm using the color diagram and removing any kind of cluster galaxies and foreground galaxies from the catalog so that we make sure we have only the background galaxies to do the weak lensing part. And once we have the weak lensing optimization done, we take the parametric mass model, which is in the core of the cluster, and then we combine it with the non-parametric mass model in the weak lensing region. So just to note here, you can see there is a hole in the center of the weak lensing region. It's because I have removed the grids from the center so that there is no overlapping of strong lensing and weak lensing in that region of the cluster. And once we have the 2 models ready, we can combine it together and get a full strong and weak lensing mass model of the cluster. So this way we have a full mass distribution of the matter inside the cluster. And here's the resulting mass contour from my strong and weak lensing analysis. And it has very well predicted the core of the cluster. We can see it has predicted the 2 BCGs very nicely. And I've overlaid the previously known substructures, previously found substructures. And it has predicted those, and as well as there are also a few new candidates. For example, this one here, or even this one. And I need to further study those candidates and see if it's actually some substructures or there's some kind of noise over there. I would like to draw your attention to the north and the northwest clumps. So these are the 2 substructures that are very, very massive apart from the core of the cluster. And there is 2 BCGs in the northwest clump, and there is some sort of activities going on there. So it's very important in order to study dark matter that we have a very high precision mass models in these substructures as well. But it's very difficult as we do not have enough constraints. So for the north clump, from the Buffalo survey, we have we have no constraints at all. And for the northwest clumps, we do have some multiple images, but we do not have any kind of SPECS or photosys to get enough to get precise mass model. And as a result, I'm going to use the JWST data, because you can already see the difference in this slide, that there is so much going on. We can see so much, we have so much more data in the JWST observations, and we already have found many more multiple images in both the substructures. And I am right now working, it's a work in progress. I'm combining both the JWST and HST data together and simultaneously working on both strong lensing and weak lensing. So my future goal will be to get done with the JWST analysis and then combine JWST, HST, and strong lensing and weak lensing for both the data. And it will help us to do more precise study of the substructures and eventually study the dark matter. And yes, thank you so much. I'll leave you with the summary.
Questions?
So just to follow up on the JWST part. So I've been working quite a bit on the JWST imaging of this cluster. And obviously you have hundreds more multiple images constraints from JWST imaging. But you should also remember the extensive spectroscopic surveys of JWST as well. So there are now hundreds of new redshifts going out of redshift 10, 12. So are you going to be including those in your mass modeling?
Oh, yes. So I have been looking into these SPECS for this cluster, and I am going to use the SPECS as well, but it seems like there are the multiple images in the north and the northwest clump still does not have enough SPECS. So I'm also taking into account photosys. Yes. So yeah, I'm already using photosys. Yes. Thank you.
So we have time for another question. And if the next speaker can please start to come up.
Not a question, it's a comment. I know it's horrible. We have SPECS from Uncover, but it was published last week.
Wow.
So I'd love to talk to you more about it. And if there's another real question.
All right.
Thank you.
If there is one last real question, we have time for it. Okay, if not, we can thank the speaker again. And I don't know who the next speaker is, but if he or she is around. I'm next. But it's different on the online. All right. So on my program, I have Dunjon Tak. All right. I hope I spelled your name. I said your name correctly. If not, apologies. So if you could please put up the slides. All right. Indirect search for dark matter with Veritas.
Thank you. Hello, everyone.
Sorry. Yeah. Slide. This is the pointer, and this is to go back.
Okay. Okay. Today I'm going to talk about the indirect dark matter search with a combined analysis of dwarf spheroidal galaxies from Veritas. This talk is on behalf of Veritas collaboration. So there was a great overview talk on dark matter, so I don't need to talk about all the details, but what I want to say is there are a lot of missing questions, a lot of unknown properties of dark matter. For example, like, is it pointer-like particle or composite particle? It can be like hydrogen-like particle, right? We don't know. And you don't know whether it is interacting with standard model particle or not, and absolute stable or not. There's a lot of questions. So there are three representative methods for studying or find dark matter. First method is collider search. Basically, by colliding the two high-energy standard model particles, we want to produce dark matter. The second method is direct search. We want to find the recoil of standard model particles from the interaction between standard model particle and dark matter. This study can be done with underground sensitive detector. And the third method is that indirect document search. That is what I want to talk about. So indirect document search is search for documentary signal from high documentary density region in the sky, where annihilation or decays of documentary produce observable particles. In my case, it will be gamma rays. So in order to perform this search, three fields work together: particle physics, astrophysics, and engineering. The particle physics to understand the process from documentary to standard model particle. Astrophysics is to determine the amount of documentary in an object. And third, engineering to find the signal, to detect the signal. So does this first particle physics can work for this part, which is documentary spectrum. And the second field can work for this part, which is J factor. And we can find the documentary signals. So this is the amount of expected documentary signal from some high documentary density region, like dwarf periodic galaxies. So I'm going to talk about each of these little bit details. The first one is, as you know, there are a lot of documentary candidates. One of them is weakly interacting massive particle, WIMP. And WIMP can decay or annihilate into standard model particle, as you can, as you can see in this sketch. Two documentary can be annihilated into double boson or ZZ boson or quarks. And after that, it can undergo some particle physics process like ion decay. And then at the end, it can produce gamma rays. So here is the documentary spectrum for documentary of 1 TeV. So if two documentary annihilate into two gamma rays, then it will produce just line spectrum, right? But if we undergo like various channels, like ZZ or something like that, you expect different kind of spectrum. So what you want to do is find this spectrum from the sky. And there are many targets, but there are a few conditions for making an object as a good target for documentary search. First one is it should be nearby system, because documentary signal should be very weak. So if it is too far from the Earth, it is hard to detect. And second, high documentary density, because the more documentary, the higher signal strength. The third, it should be free from other sources of gamma ray emission, because if there is a bright source at the center of like documentary halo, we cannot distinguish the emission from that bright source from documentary signals, so that it is hard to find the documentary signal. And dwarf periodic galaxy has a good property. First, there are documentary there, and it is 10 kiloparsec away from the Earth, so it is quite nearby. And mass to light ratio is quite large, which means there's a lot of documentary there, and there's no known background sources. So we want to observe dwarf galaxies with this telescope, very energetic radiation imaging telescope array system, VERITAS. VERITAS consists of 4 12-meter IACT located in Arizona. IACT means Imaging Atmospheric Tranquil Telescope, which means basically, imagine there's a very high energy photons, and as it enters the atmosphere, it produces tranquil light. And by observing that UV light, one can reconstruct the direction and energy of the primary very high energy photons. So the energy range for this VERITAS is 85 GeV to above 30 TeV, which means it is good telescope for studying WIMP, because WIMP has a mass around few TeV. And it has field of view of 3.5 degrees, and it has good energy and angular resolution for documentary study. So this slide summarizes our method. So we are looking for WIMP signal from dwarf periodic galaxies with VERITAS. So this slide summarizes our observation. We observed more than 600 hours of observation for 17 dwarf. And here are a list of dwarf. And you can see that the number of events from the dwarf and the event from background region and exposure time, size of region, significance, and flux upper limit. I want to mention that compared to our previous study, which is in 2017, we extend the observation time about 3 times. Like previously, we have 220 hours of observation, but now we have more than 600 of observation. And we also improve our technique, especially for reconstruction pipeline with boost decision tree and other techniques. And then as you can see, I marked 3 dwarf, SIGA 1, Ursa major 2, Ursa minor. For this dwarf, we have longer, deeper exposure time because they are expected to have more dark matter compared to the others dwarf. So here is this table summarizes the J factor from 17 dwarf. And you can see that SIGA 1 and Ursa major 2 and Ursa minor has much larger J factor compared to other dwarf. And you can see that there are 2 J factors. One is from under 20 and the other is from GS 15. And just 15 is widely used for indirect dark matter search, but we adopt the recent work by Ando because they compute the J factor with more physically motivated prior. So we think that is more accurate dark matter, more accurate J factor. And as you can see here, GS 15 tend to have higher J factor compared to under 20. You can see the ratio. Ratio is higher than 1, which means the estimate from GS 15 is higher. So if we take the under 20 with the same data set, we expect less signal, right, from dark matter, so that we can set less stringent limit, but more accurate limit. Definitely, we don't have a signal, but we can set an upper limit on dark matter cross-section. So this figure shows our upper limit for tau channel. Basically, we assume that 2 dark matter are annihilated into 2 tau plus and tau minus. And here, the blue one is our median. And this uncertainty band is from J factor. If you go back this table, you can see the error, right? Error size. And the uncertainty from J factor is the most significant systematic error for this dark matter search. So we focus on this systematic error. And you can also see the upper limit from an individual dwarf. And the figure on your right-hand side shows the result. And in this case, we test null hypothesis. Basically, instead of using the observed on-region event, we randomly sample the event from background and compute the upper limit. And as you can see, the band, our limit, which is blue, is consistent with band, which means our limit is consistent with background fluctuation. This supports that we don't see any dark matter signal. And here is the comparison with our previous work. Blue is our limit, and black dashed line is from our 2017 work. And you can see that there is no significant improvement compared to our previous work. It is because we increase the data and we improve the method, but we take the J factor, which is smaller than the one we used in the 2017. So if we use the same J factor, we expect to get this orange dotted line, so which is much better than our previous work, but we stick to use the one more accurate, which is Ando. So these 2 effects are canceled out so that we have more or less similar limit. And here is the comparison with other work. So you can see Hawk, Magic, and Has result. And our limit is compatible with the result from other IST. I'm not sure I have a time to explain this slide. Okay. So we also set some constraint on ultra-heavy dark matter models. So basically, instead of point-like particle, WIMP is like point-like particle, right? But we can assume some composite particles, like hydrogen-like dark matter. Then we can set the limit on its radius. So from our limit, here is the exclusion region, so that if assuming that ultra-heavy dark matter mass is less than 1 PeV, then its radius should be smaller than that for proton charge radius. So that's it. Thank you.
Questions?
Thank you very much. Taimur Seyfullah, Observatory of Strasbourg, and I have a general question, and please feel free to tell me if it doesn't make sense, the question. So you showed this plot with all the constraints on different properties of dark matter, different works, and if I understand correctly, everything is based on an assumption that dark matter is one kind of particle. And you also mentioned, well, we also know that it can be a family of particles or different particles. But then in that case, if it is indeed a family of particles that we're talking about, how one can interpret those constraints? Do they make sense? Or maybe we should think about it a bit differently.
Yeah, so we can test various kind of dark matter, but I don't know, I have a slide for that. We have to go back to very beginning. So this is the part you are concerning, right? How this part can be changed as if that is different kind of dark matter, right? So actually we can, so in this study, we assume that all dark matter are annihilated into one of these channels. But if it is like it has some specific model, then it can have some ratio, like 20% can be annihilated into double boson, and the others undergo some ZZ channel or something like that. So we can test various kind of models, but in this work, we assume that all the dark matter are annihilated into one of the channels. So in case of Wino, which is one of the dark matter candidate, in that case, it has specific channels. So we also test that kind of model. So if you can give me any kind of dark matter models, we can test it and then set a limit on that. So yeah.
We have time for one last question, but please feel free to continue the discussion on Slack, and if the next speaker can start approaching the stand.
There is a plot which you varies H0, the Hubble constant. What does that mean? Does that...
Oh, not Hubble constant, is another hypothesis. So, sorry, maybe that's confused, right? Sorry, H naught means null hypothesis instead of the Hubble constant. Sorry, I have to mention, but I forgot it.
Sorry because it looks obvious. It's Hubble constant.
Yeah, sorry.
Thank you. The next speaker is Michael Sarkis, that will talk about dark matters. Yeah, thank you.
Yeah, no problem. Okay, great, thanks. Hi, everyone. So I'm Michael, but I'll also be giving this talk on behalf of Jeff Beck of Wits University. He's been steering the ship since the project began. Unfortunately, couldn't be here in person. So let's start off with the question of what's the matter. We have seen in the previous talks some basic information about this. We know that there are a bunch of, there's no shortage of dark matter candidates in the literature. They've all gained some popularity at some point due to their weird and wonderful personalities. And we know that WIMPs are still not fully ruled out. It's quite difficult to rule out a full class of particle models. So we need to keep looking. And one way we can do that is with indirect detection. Luckily, we've had some excellent talks previously which have gone over this, so I'm not going to spend too much time, but we'll look at these WIMP-WIMP annihilations as before and observe the standard model products that they produce. Okay, so what I've done here is just collect a few highlighted works that have looked at this indirect detection for the radio and then for a bunch of other multi-wavelength and multi-messenger products like gamma ray, neutrino, and cosmic ray telescopes. And what we see from these plots is that there's not only just a lot of work going on to try and detect these dark matter particles, but that we're also getting quite close to probing this thermal relay cross-section. So what these plots are showing is the annihilation rate, which is telling us how often these WIMPs will annihilate with each other. And if they cross this thermal relic line and produce less emission than what we see with our observations, we can rule out that particle as reproducing the abundance of dark matter we see. So I'll jump straight into what I'm going to call the workflow of this code that we've been working on for a long time. So what we'll do is we'll all types of physical properties of the thing that you want to model. So this includes things like a dark matter halo profile, and for my in-body simulation halo friends in the audience, I'll specify this as a static halo of a virialized dark matter halo. We also can see things like the magnetic field and all of the particle annihilation spectra, which in the last talk was spoken about quite a lot. If there's any other profiles in the future, this is quite easy to add to the code. As we saw in a talk earlier, there's lots of work going on to try and figure out exactly what the very inner regions of this halo looks like. So this we can add at any point. There's the last thing we need to specify is which type of output we're interested in. So we've got some multi-wavelength options here. We've already heard a lot about the gamma ray results, so I'm going to focus on the radio. And not only for that reason, but also this was my main contribution to this project, was figuring out the radio. And it's also a lot more difficult, which is why we don't see it as much in the literature, because for those not familiar, the exact mechanism we're looking at here is synchrotron emission from electron and positron pairs that are created through the WIMP annihilations. So these electrons and positrons will be injected into the dark matter halo, and if there's a magnetic field in the astrophysical target that you're looking at, these electrons and positrons are going to spiral around, and as they do so, they'll emit synchrotron radiation, which peaks in the radio band. The reason this is a little bit more challenging than gamma rays, which aren't affected by the magnetic field at all, is that these electrons and positrons are subject to diffusion and various mechanisms of energy loss, and we'll talk about those shortly. So my original plan was to do a live demo of the code, and then I thought that's probably an easy way to make something go wrong. So instead, I just have a little video, so don't blink or you'll miss it. So what we do is I already missed it. You very simply just run a run command once you have that input file, and it's already complete, and it runs all of the calculations for you very quickly. So this is one of the important features of the code. So now that the calculation is done, I'll just go very briefly over what's, I feel, the important part of the code is this electron transport, which deals with the spatial diffusion, the energy losses, and then obviously the source of electrons and positrons in the halo. We solve this in a numerical way with finite differences. This is one of the main differences to an existing piece of code, which is called RxDMFit. And because of this numerical solution, with a couple of nifty features that we've added in, like using SciPy's sparse matrix libraries and a vectorized block matrix implementation, we see that the code executes really quickly. And this is important, especially if we're coming into the age of big data in astronomy, and when you're looking at surveys, it can be quite a hassle to look at different density profiles, different annihilation channels, and repeat these calculations for tens and dozens of targets. So we feel like this is really important. It also is more accurate because of this numerical technique. We find that if you don't use numerics, you need to make some approximations about the magnetic field. What this does is underestimate the central region of emission, and it also allows the electrons and positrons to diffuse further out throughout the halo. Thanks to Andrei Egorov, we've also done a little study on the energy loss mechanisms, which we can see in this plot. Some of the Bremsstrahlung energy loss formula of the past were not correct. So we've changed those and updated those, and this is all baked into the code. Once it's finished, we have some output files. I'll just very briefly highlight some sample calculations that we've done here for the, this is SED for the radio and prompt gamma rays and secondary gamma ray emissions. We've also got surface brightness profiles. So this is over the entire halo region. In the radio, we've got integrated fluxes as well across the whole halo over the frequency range. And we've also included functionality for these FITS data formats, which are used extensively in radio astronomy. So briefly before I finish off, I'll just highlight some of the work we've already used this code for. So we've done some work with Meerkat observations. I don't think I need to introduce Meerkat at the end of this conference. And this was done with the Meerkat Galaxy Cluster Legacy Survey results. So this is all public data that I did with some collaborators. So Natasha Lavis is here in the audience. Jeff obviously couldn't be here in person, and Kenda, I'm not sure is here. I haven't seen her, but she worked with us on this as well. And there's we released a paper on this last year that showed all of our results. Our technique here is to take a Meerkat continuum image from the telescope. We remove all the foreground sources using some techniques. It's extremely valuable to have faint galaxies, and the Galaxy Cluster Legacy Survey allows us to look at a bunch of different clusters, some of them more faint than others, but each of them go through this process. We remove the foreground sources. We generate a model, generate model emissions using our code package, and then we compare these two, as was seen in some of the previous talks, to generate these limits. As you can see, some of these are extremely stringent on this thermal relic cross-section. In our best case scenario here, where we use a standard NFW halo profile through bottom quark annihilation channels, we see that we can probe this thermal relic cross-section for almost the entire electroweak WIMP mass range. This obviously will change depending on the precise modeling scenario you want. So as we get better magnetic field profile data and dark matter density profile data, you can get some variation in this. And these results are sort of less optimistic if you're using a shallower cusp in the dark matter halo density profile. So I think I'm finishing a little bit early, so I'll finish off on this slide and say, as of yesterday, our code has been open sourced, and I got an article up on the archive. It's been a very busy month for me, and hopefully you can take a look and help us improve it. So thanks very much.
Yeah, there is a question over there.
Hi, Eric Tylerud, Space Telescope Science Institute. I'm really glad to see your willingness to talk about just a code in a setting like this. That's really good. But I did have a question, which is, you described a workflow that was focused mainly on files coming in and files coming out. Is it also usable embedded in other codes? Can you use it directly from a programmatic interface, or does it really require files in and out?
So yeah, thanks for the question. So that's currently how the code works. It's written in Python, and it just basically requires us a couple of commands to input those files and perform the calculations. We do what's the word? We outsource some of the harder work, like for all the particle spectra. We interface with other code packages and recipes. yeah, that's how the code works at the moment. There's always chance to adjust it in the future if there's means for it. Yeah.
Any other question? Yeah.
Thanks for a great talk. I have a very silly question. Are these synchrotron emissions you see, could they be contaminated with other sources of synchrotron emission and in general with other things in the same radio wavelength? Compare if you want to get a dark matter signal from the other sources.
Yeah, it's a good point. One of the hindrances to using radio emissions for dark matter searches has been the baryonic component. That's extremely difficult to model. Our strongest results come from meerkat images of galaxy clusters that are extremely faint. So if you can find a target that doesn't have lots of foreground emissions of things that you can model, because we expect the dark matter distribution to be very diffuse. So if you see things like jets, it's quite easy to take out, but there's some issues. So the baryonic component is a big issue, but looking for nice sources, especially with high resolution telescopes like Meerkat and the SKA, that will help a lot in the future. Yeah.
All right. We have to move on. We are going to have 2 short talks now of 3 minutes. There won't be questions after the short talks, but please ask them on Slack or go see the posters when they are available. And I should also remind you to please stay in the room at the end of the session because we are going to take a picture. So if you want to be in the picture, stay around. And is it you, right? Samuel Lange, if you could please put on the presentation.
I mean, you've just seen my entire presentation. So. Yes, hi, my name is Sam Langer from Durham University. I'd really like to thank the organisers for giving me this opportunity to talk about strong lensing. Now, we've heard a little bit about this already, and specifically what I'm doing is looking for dark matter substructures using strong lensing. With the aim to thereby constrain the subhalo mass function and the nature of dark matter. I don't have time to get into the specific methodology, but please do come and talk to me afterwards. The key thing that you need to know is that when we're modeling a galaxy lens for the mass distribution of the lens, we normally use a smooth elliptical power law mass distribution to make that model along with some external shear. What we're now doing is also adding angular complexity to these mass models in the form of multipole perturbations. And after that, and before that as well, we add these substructures in a Bayesian framework to see if the substructures are needed for a better model fit. So I'll go back and say we're looking at 2 JWST lenses, SPT 2147 and SPT 0418 here in multiple filters. And so our key results that you can see most of is that if we look on the right-hand side here, these are our subhalo grid maps. These effectively show that when we put a subhalo in some certain position, how much does it improve the fit? Effectively, red squares there is very, very strong Bayesian evidence for a subhalo here. Yellow squares means, yes, you should look here. Blue squares mean, yeah, okay, kind of evidence, but probably your mass model just needs a bit of improvement. And the key thing to note is that our 444 base model, this is the elliptical power law plus shear. We have a very, very big red area to the east of the center of the image. That goes away when we add these multipoles, these angular perturbations, effectively showing with real data what has already been shown in the literature, that multipoles should reduce false positive subhalo detections. However, we remain with some kind of subhalo signal to the top of the image, even in very angularly complex, that's not a word, angularly complex mass models. And if we look over here, what we're seeing is that our base substructure model is an incredibly, incredibly strong Bayesian evidence. But once we add the multipoles, the evidence decreases, but there is still evidence within some confidence region for substructure here. We contrast this with the other lens where we don't get anything. So it shows that it's not adding multipoles for multipoles' sake. So yeah, that's everything. Please do come and chat to me. Come and see my poster. I'm on screens 59 and 52. So yeah, thank you.
All right. The last speaker of the session will be Marie Corsaga. If she could please approach the stand. She's going to talk about the H1 to halo mass relation for isolated disk galaxies. Presentation backup, please. All right, thank you. 3 minutes.
I'm sorry. Hello, my name is Marie Corsaga. I am an assistant researcher at University Joseph Kizerbo in Burkina Faso. So I'm going to talk about a work that I conducted in collaboration with Benoit Famé, Jonathan is here, and Lorenzo Posti and et al. So it's we published it last year. It's about the scaling relation, about the H1 mass and the halo mass for in the isolated disk galaxies. So we know that scaling relation as between like baryons and dark matter global properties are key to shed light on the process of galaxy formation and evolution. So most of these scaling relation either focus on the baryonic to Tully-Fisher relation or on the stellar to halo mass relation. So less attention has been paid on the relation between the cold gas and the dark matter contents. And in this work, we focus on the relation between the H1 mass and the dark matter halo mass. And yes. So for this, I don't know, it's not, doesn't, yes. Yes, for this, what we did is we studied with mass distribution using a sample of spark data and little things data. So we combine the kinematical data, that means the extended H1 rotation curve with the photometry data, and then we construct the mass model. To construct the mass model, we use two profiles. So the standard NFW profile, and then sorry, I don't know why it's the standard NFW profile and the Dekel-Zhao profile. And for the Dekel-Zhao profile, we have we constrain the dark matter profile using 3 parameters: the inner slope, the concentration, and the halo mass. And after that, we have a different parameter for the dark matter halo. And then we now explore the relation between the halo and then the H1 mass. And here I am presenting the different scaling relation. You can see the H1 mass as a function of the halo mass. And then we found a linear relation between the 2 parameters. And when we look at the right hand side panel, the ratio between the H1 mass and the halo mass as a function of the stellar mass, we didn't find a correlation between the 2 these parameters. And when we compare with the simulation, we use the Illustris TNG and the SIMBA simulation, and then you can see like a turnover at the high mass. Why we don't find it in the look when we use the observations. And also for the bottom panel on the right hand side, you can see that we have a turnover when we like showing the ratio between the H1 mass and the halo mass as a function of the stellar mass. while in the observation, we didn't find the correlation. So we try to understand why we see this turnover on the simulation and not in our observation. We said that maybe we need to find these galaxies in the simulation. So we selected these galaxies following different criteria. And then we found at high mass, for high massive galaxies, and then we found that they follow the relation, the trend like the other galaxies. So that means it's not depend on the morphological types, the result that we found, because these galaxies also follow the trend in simulation. But we found that we didn't find this trend in our observed galaxies. And also we check if maybe it's because of AGNs. So we also selected galaxies that oscillate AGN in our sample. And then we found, you can see the blue square are galaxy Austin AGN. And then we can see that they don't really follow the trend. And the green band is the simulation from SIMBA. And yes, so in conclusion, I can say that, okay, observe rotationally supported, these galaxies can be, okay, the ratio between the H1 mass and the halo mass as a function of a stellar mass and independent of morphological types of galaxies. So I think I will stop here. If you want to know more about how it works, I'll be happy to discuss with you and then to get questions. So.
Okay, so I would suggest one more applause to thank all the speakers of this session. And please stay here for the picture. I'm not sure how it's going to happen, so I will give the mic to Jonathan.
No, I think it's going to happen, and that we're going to, the idea would be to move next to here. So we have the poster of the focus meeting at the background, and the photographer is here. So everyone who wants to be on the picture, just move towards the screen.
Hi, cracking on it. Hi, that's okay. It's good, I like it.
Yeah, that was Jim's slide.
I like it.
Okay, so we're resuming the session by the first talk, which is online, Julia Despali about galaxy formation in alternative scenarios. Are you there, Julia?
Yeah. Hi, can you hear me?
Ah, good. Yes, you can hear you.
Great. I'll share my slides then.
Yes, we can see. Yes, it is in full screen.
Okay, perfect. So yeah, hi everyone. And first of all, I want to thank the organizers for the kind invitation. And yeah, I'm really sad that I couldn't travel to South Africa to be there in person. But hopefully I can still provide some excitement about what's happening in the galaxy formation community in alternative dark matter models. So I realize this is quite of an ambitious title, so I apologize in advance if I don't cite some work of some of you, but I try to do my best given the time available. So what I'll do is try to give a short overview of what are the most common effects of alternative dark matters, which in this case will be like warm and self-interacting dark matter, which are the most commonly used in numerical simulation, and then hopefully provide some excitement for what's happening now in the computational world to study galaxy formation in these scenarios. So first of all, let's start from what we really know very well, which is the large-scale structures. So although we don't know what dark matter is, as have been said many times, simulation predicted this cosmic web structure that we all know about with halos and filaments and walls, and this has been observed in the galaxy distribution. For instance, here is the SDSS survey of the Vipers survey. So we see galaxies as tracers of this cosmic web structure. So we want every dark matter model to reproduce this. So cold dark matter does this very well. And this is one large-scale structure constraint from alternative models. So they have to keep this structure on large scales. What we don't know so well is what happens on small scales, for both from the point of view of baryonic physics, so models, subgrid physics, and models of galaxy formation on small scales, but also the distribution of dark matter. So when we look at single galaxies at very, very high precision, there is room for changing the dark matter models there, and there's a bunch of tensions that still exist between observations and prediction from cold dark matter simulations. So of course, there's many possible theoretical alternatives to cold dark matter and to lambda CDM. I would say the most common that I use in simulation are two, and so historically the first to have some success was warm dark matter. So for people who don't work on dark matter models, so this is a model where particles are lighter. So if CDM we think is made of by WIMPs, so GeV scale particles, warm dark matter particles are much lighter, so the kilo electron volt scales. And so this lower mass implies a higher velocity. And so then the dark matter particles don't cluster so easily and don't form as many low mass structures. So here is the halo mass function. You can see a suppression at the low mass end. And this suppression increases for lighter particles. So lighter, warmer models predict less and less structure on small scales. And this is true at all redshift. So change evolves with redshift, but it's always true. And so compared to CDM, this leads to a set of effects. So the most obvious is that you have fewer satellites and low mass halos. So as in this famous simulation by Mark Lovell that everybody always shows. On the left is the cold dark matter halo hosting a Milky Way galaxy. And on the right, a very warm dark matter. You can see only the higher mass substructures survive and everybody else is washed out. So this is obvious, but the fact that things don't form, of course, also has implications on larger scales. So it has been shown, for instance, that since there is not so much matter in the substructure, there is most matter in the smooth halos, but also larger amount of matter in filaments and walls. So Richardson et al. In 2022, for instance, has shown that this larger amount of matter in filaments can have an impact of gravitational lensing and flux ratio anomalies compared to CDM. Since this suppression is there at all scales, this also influences structure formation. So we know structure formation is supposed to proceed hierarchically. And so if there's fewer smaller structure, then there will be a delay also in the formation of higher mass systems. So here it's another more recent simulation by Mark Lovell, shown the dark matter distribution of redshift 10. And so even at this high redshift, we have less structure in warm dark matter, which I believe here is a 3 keV model. And so why this is important is because now telescopes are starting to probe high redshift. And so measurements like this are important to compare to stellar mass function, for instance, compared to observations such as the JWST. So in general, this delay of formation of small-scale structure in practice has an effect on many things. So the matter power spectrum, satellite counts, gravitational lensing, as I'm sure John will talk to all about, or the Lyman alpha forest. And all these studies have been used to put constraints on how warm this warm dark matter can be. And so here's an example of such constraints. So each line is a separate study, and on the x-axis you have the mass of the warm dark matter particle increasing to the right. So to the right, we go towards cold dark matter if you want. And so these are all upper limits, and the two vertical lines correspond to the lines of the same color on the left. So 3 kilo electron volt is still at the edge of being okay, but it starts to destroy too many structures that we are actually observing in the universe. And the most current constraints believe it's more around 5 keV. So warm dark matter in constraints is now not as warm as we thought it could be initially, but 5 keV is still a lot warmer compared to 1 giga electron volt for WIMPs. And so we expect that when telescopes will become high resolution and we have better and better observation, we'll be able to probe also this mass regime. So after warm dark matter, the next favored alternative model, I would say, in the simulation community is self-interacting dark matter. And although these plots can look similar to the one just before of the mass function, it's actually something different. So these are halo profiles. And while in cold dark matter, halos famously follow on average the NFW profile, the main signature of self-interacting is changes in the density distribution inside of halos, because particles interact with each other. And so in very high density regions, they can exchange momentum and energy. And in practice, they scatter a lot at the center of halos, and the particles are then sent away from the center, creating a core. So the basic effect of SIDM is, as shown here, to create a core. Although this is true in all dark matter only simulation, but it can vary once you add baryons. But then surprisingly, maybe if you've never heard about this, in some cases, so where this self-interaction cross-section is high and is very, very high, or thanks to tidal disruption and the inclusion of baryons, this core formation can be followed by actually a density core collapse at the center, which can create Caspier profiles than in cold dark matter. So self-interacting dark matter is actually a family of models that can lead to very, very different effects depending on the scale, depending on the strength of the cross-section. And so we can have cores, but we can also have cusps, as shown here. So the cyan points are, sorry, the white points are cold dark matter, and then the yellowish point are the self-interacting values. And you see there's an increase in the mass within the very, very inner part of the halos. So this can, again, influence galaxy formation in different ways, and measurements such as strong gravitational lensing, which is really dependent on the density at the very center of structures. As have been already mentioned today, I think, so self-interacting is also one of the best candidates that have been tried to explain the diversity of properties of dwarf galaxies. So here's a plot by Camila Correa, who found the cross-section that best fits all the dwarf spheroidals in the Milky Way, for example. And a very flexible SIDM model is able to explain this diversity and also in the rotation curves of galaxies. SIDM can also then cause, because of these changes at the very center of halo, differences in galaxy dynamics and bars, and it can then also make halos rounder. So these interactions that change the density profile also, of course, randomize the shape of the halo at the very center. And so the ellipticity of halos is higher in cold dark matter than in self-interacting dark matter. And this is another observable that has an effect also on the baryonic distribution, for instance, on the diffuse gas inside a halo. And finally, at the higher mass end, if dark matter is self-interacting, it has an effect on cluster mergers. So here shown is two different self-interacting models. So the one on the right is more self-interacting, and what is shown is the offset between the dark matter and the galaxies as a function of cosmic time, so which is a tracer of objects such as the bullet cluster. So if there is self-interaction between dark matter particles, this will create a lag, which is more or less pronounced compared to what expected in cold dark matter. So again, in this case, maybe self-interacting dark matter is more complex as warm dark matter, and it can have an effect on a larger variety of scales. And this is why constraints actually span many order of magnitude in mass. So this is a plot that shows the self-interaction cross-section on the y-axis as a function of velocity. So velocity is the particle velocity, which correlates with the mass of the object. So particles in galaxy clusters are around 10 to the 3 kilometers per second. And then when you move to 10, it's more the scale of dwarf galaxies. So all the points are upper limit that tell us that dark matter cannot be extremely self-interacting at the high mass end, because we don't want to see cores at the center of galaxy cluster, because we know they're not there. Otherwise, galaxy cluster will not produce the beautiful gravitational arcs that we see, for example. On the other hand, at the low mass end, the self-interaction cross-section is allowed to be high to explain this diversity of properties of things like the dwarf spheroidals. And so the favored model of SIDM at the moment, I would say, is something that looks like the yellow curve, or variation of it. So models where the self-interaction cross-section is not constant, but it depends on the velocity of the particle. So if the velocity is very high, then particles are unlikely to interact. And so in clusters, we keep the main properties that we know. Instead, if the velocities are low, particles interact more easily, and so they can create different systems such as dwarf galaxies. So these are the two main mod alternatives that have so far been used a lot in computational astrophysics. But of course, these are only two of the possible models that have been proposed. And there starts to be constraints on some of these models, but we still don't know what dark matter is. We still don't have definitive proof. So the best would be, of course, to increase the number of models that we explore, and then to try to really put constraints comparing predictions with observations. So now we'll move to talk about a bit what we are doing in computational, from the computational side, compared to what is available now in cold dark matter. So this is a plot from the TNG collaboration that summarizes simulation in cold dark matter that were available at the time of the first TNG papers. And it's useful to show that they separate in two main regimes. So on the top left, we have the zoom regime, which is very, very high resolution simulation of a few objects, so a few individual objects. And then at the bottom right, we have instead the cosmological simulation, which are large boxes. They cannot be at the same high resolution because of computational time reasons, but they're very useful to collect many systems. And so the cosmological simulation can give us something like this. So many, many galaxies that hopefully at some point will reproduce the diversity of observed objects. And instead, zoom-in simulation gives us very detailed view of individual objects, nowadays in some cases, down to even almost single stars. So we have many cosmological simulation in cold dark matter.
5 minutes?
Yeah. So this is a list of what is available. And so there's many, but if you look at the years, they're all been released in the past 10 years. So we should remember that up to 10 years ago, it was very hard to make realistic galaxies in simulations. So we will hope that at some point we will reach this same level of precision in alternative dark matter models, because we have seen already, indeed, in this session, many plots where observation and comparison to things like the TNG, for example. So what's happening in the worm and SIDM cosmological simulation is this. So there's many zoom-in simulations that were too many to plot here, but there's not very many, up to now, there were not very many cosmological runs. And so the gray ones include only dark matter, while the one in color start to include the effect of baryons, which is important to then produce realistic prediction. So there's the Thiessen simulations, which is very good to look at the effect of reionization, a redshift larger than 6. Then there's the Tango SIDM simulation by Camilla Correa, which are 25 megaparsec boxes in SIDM. And then I want to highlight some new projects. So this is the AIDA TNG simulation, which is something I'm leading together with other collaborators from the TNG group. So this will be 3 cosmological boxes run with both warm and self-interacting dark matter models. So hopefully we will have many galaxies to compare to observation. And then recently there was a paper of this new DREAMS project, which is again a set of many more 25 megaparsec boxes with many variations on dark matter and baryonic physics to also train machine learning models. But what is important is that all these new simulations are now starting to populate the same parameter space that we have well covered in CDM, and they all have different prescriptions from baryonic physics, which is crucial to be able to really disentangle the effect of alternative dark matter and baryons. And so why is this important to look at cosmological simulation? Just a brief examples from our past work. So we had simulated elliptical galaxies from the TNG simulations, like 10 galaxies chosen to be analogs of gravitational lenses. And we found that some of them, so the very high mass end, formed a core in SIDM. And this caused the fact that the lens images were smaller than in cold dark matter. On the other hand, we found that some of the lower mass end had a cusp in SIDM, which is an effect that has been found also in other works at the Milky Way scale. And so the Einstein radii were bigger. So we thought, okay, maybe if these are representative of the entire population, then we will observe, for instance, with Euclid, a very different Einstein radii distribution, different sizes of the lensed images. But then we repeated the same thing with the Eagle SIDM simulation, so a 50 megaparsec boxes with many more systems. So instead of 10, we had 150 or 200 systems, and calculated the Einstein radii of the system and found that when you looked at many more and diverse systems, then the difference is actually not that big. And so this is why it's important to have cosmological simulations in alternative dark matter and with baryons to be able to really look at the diversity of systems. And so now just some very preliminary results from our new simulation. So with 3 boxes, we can look at statistical properties, such as the halo mass function. So on the left, you see the general halo mass function. So you see that the warm dark matter models in purple and yellow suppress the mass function as is expected, while the green SIDM models don't really change it. And on the right, what you see is the ratio of the hydro to the dark matter only run that we have for each case. And so it's well known that also already in cold dark matter, baryons suppress the halo mass function. We see a very similar trend in all dark matter models. So in this case, at least in this statistic, it seems that the baryonic physics wins. So the TNG model is not being changed between the runs. So it's always the same. And one could ask, is this fine? Should we recalibrate things? So for large scale statistics, it seems that things are fine, but we can also look at galaxy properties now. So things like the effective radius of stars as a function of stellar mass. And here we see some differences. So for instance, we see that low mass galaxies in stellar mass have slightly bigger effective radii in SIDM compared to cold dark matter, which is similar to what Camilla Correa has found in the Tango SIDM simulation. So it's reassuring that despite the differences in the baryonic physics model, we kind of see similar things. And so I'm going to skip this. So these are these were examples of large statistics. We can also look at individual halos and zoom really into its properties. And so when we measure things like density profiles, we see the effect. So even if the mass function is the same, so even if the number of galaxy cluster of massive halos is not suppressed in these alternative models, their internal structure is different, and self-interacting dark matter produces a core, even in the presence of baryons. And we can do the same exercise of many orders of magnitudes, so from 10 to the 11 to 10 to the 15 solar masses. And what we observe is that in very high mass halos, where the baryons are not the dominant component, self-interacting dark matter is able to create a core. And so this will be a very good indicator to constrain some of these models. And instead of the low mass end, we see that the profiles are similar, but maybe there is a slightly increase at the center. So maybe we're seeing some signs of a cusp in Milky Way systems and below, which is something that also has been seen in isolated simulation of Milky Way galaxies, also done with the by John Arrows with the TNG model. So they also saw that in cold and SIDM models, the structure of the Milky Way type galaxy with arms is able to form, but is slightly different. And the slope of the internal profile is steeper in SIDM than in cold dark matter. And then just to conclude, these galaxies look very similar, so it's nice, all fine. But the beauty of having large scale simulation is why we can also look for strange objects and investigate why, in some cases, things change. So if we zoom on this galaxy that I showed at the beginning, for instance, this is the gas density of a Milky Way sized galaxies in cold dark matter. This is how it looks in a self-interacting dark matter with a velocity-dependent cross-section. So we're not really sure already why this is happening, but we believe that the self-interaction at the center change the structure enough that some spirally things is forming, but it's way puffier and it's more diffuse. And then the same object in another SIDM model with constant cross-section looks like this, and is yet different in warm dark matter. So there will be hopefully many systems that show some difference, because this will be the most exciting thing. So I think
zero time.
Yeah, I'm over. So I think the galaxy information future in alternative dark matter models is very bright. And so in the upcoming years, there will be all these new simulations, which hopefully will be released, and which will really allows us to probe many orders of magnitudes in mass and compare them to observations such as in surveys and so on. And just as a last slide, I just wanted to advertise that our new simulations are now ready to be used. So we'll publish the first paper soon, but get in contact with us if you're interested in using them. Thanks.
Thank you very much. I'm afraid we have time only for one question. Is there one? Yeah.
Thanks, Julia. This is Azifat Tahi from Durham. One of the last points you mentioned on the Milky Way scale, whether you get, once you include the baryons, whether you have a core, a SIDM core or not, I think perhaps depends on some of the subgrid physics or galaxy formation, because an Eagle or a Pulsar, we see at those scales, they have a core, but I can totally see if the baryonic physics is slightly different and the baryons are a bit more concentrated, they can accelerate the core collapse. Do you have any suggestions how we can perhaps break this degeneracy that kind of move forward? Do we expect like a core in something like Milky Way or not?
Yeah, that's a good point. And indeed, I mean, I think that's why it's good that different groups are now running simulations with different models. And then at some point, we'll be able to compare if the dark matter alternatives are the same, but the physics is different. Yes, I mean, it can be driven by the baryonic physics. And indeed, when I've seen it most prominently was in using the TNG, but also, so in this plot that I showed from the Eagle, it's true that we here. So it's true that we recovered like the same distribution of the Einstein radii, and I don't have the density profiles. But there were some cases also here where the density profiles of halos was a bit steeper in SIDM than in cold dark matter, but these were higher mass, so we're like 10 to the 13, not Milky Way. So I really think we will know more soon. I mean, the ideal thing would be to vary both, like to have samples of a simulation where you change both the dark matter models and tune differently baryonic physics, but it's very expensive. So I think hopefully we'll be able to combine works by different groups. And this will help.
Thank you, Julia, again.
Thank you.
Now we have Azadeh Fatahi, who will speak about galactic halos in alternative dark matter models. Which? Oh, sorry. Sorry. Okay. So I'll give you some.
See if I can learn how to move forward and backward. I guess the green. Good. Oops, already too far. Let's try to go back. Maybe. Okay, that's better. Hi, everyone. I'm Azadeh Fatahi. I'm from Durham University. First of all, thanks to the organizers to organize such a fantastic session that I personally learned a lot, and also for the opportunity to talk a little bit about the galactic halos. Actually, I was a little bit surprised. There was no other galactic halo talk, so I'll try to give a little bit of maybe 1 or 2 slides of introduction, what the galactic halo is. And thanks to Julia, actually gave a very nice introduction about alternative dark matter models. So it's going to make my job easier, so I don't have to go over some of those basics. The picture you see on the right-hand side is what we call a stellar halo around something like the Milky Way. But let's have a quick recap of what is the importance of stellar halos to understand dark matter. Some background is basically in the lambda CDM or even some alternative dark matter models, the galaxy formation happens hierarchically. It means the smaller objects get accreted to the bigger ones. And as this happens, they can form basically an extended stellar halo around objects. A movie can presumably show this much better. Something to have in kind of keywords to have in mind. These are the consequences of the hierarchical galaxy formation. And also the fact that there is the power spectrums of matter. Basically, we have power all the way to the smaller scales, and we have a smaller kind of dwarf galaxy type of dark matter clumps around. And this is a movie from the Eagle simulations, just to give you a mental picture of what this hierarchical galaxy formation looks like. And you're seeing in dark matter, gas, and stars, and the different gas, stars, and dark matter, and how a galaxy is essentially coalescing from the smaller objects. And as you see, what the dark matter is, of course, maybe you've seen more of that picture, but also the stellar light is also, you have lots of the smaller things that are being orbiting, and some of them disrupted to form a stellar halo that would look like something like these panels. So here is an example from another simulations. You have two halos in dark matter that would look like something like Milky Way or Andromeda. And if we look at the stellar light, changing the contrast such that the low surface brightness features will come out, we see an extended stellar light around galaxies such as Milky Way, which are formed from the disruption of the smaller objects. Actually, if you squint, maybe you can see some substructures around these. There are some tidal streams there. Maybe you can start to see some shells. So these are formed from basically disruption of the smaller objects. And the smaller objects are the key point to understand these stellar halos. And this is in the simulations. Observationally, also, we have seen a stellar halos. The examples, we can see Andromeda on the left with lots of like tidal features and substructures, another big elliptical galaxy with its kind of the extended stellar halo around. So we want to understand basically the connection between this diffuse stellar light and presumably the dwarf galaxies and the dark matter, the smaller dark matter clumps that got disrupted and formed this stellar halo. If starting with CDM, so I give like one slide of what it looks like in the CDM and then contrast it with what, if we change the flavor of dark matter that affects the smaller scales, does it affect does it change the properties of stellar halos? This is just one example from Auriga simulations, but that it's not too simulation dependent. These are the regimes we understand. We can look at the number of objects that have been destroyed and form this diffuse stellar halo around something such as Milky Way. Different lines are different halos, and the kind of the thicker red line is the average of number of destroyed objects that have formed these stellar halos. Something to have in mind, as perhaps not surprising to some of you, there are more of smaller objects and fewer of bigger objects. This is essentially the halo mass function and the stellar mass function. We have more of smaller things, so that is not perhaps surprising. Something to contrast with, at least that wasn't known when we were looking at it. Actually, the number of destroyed ones is on average bigger than the number of survived objects. And these survived objects are the ones that at present day we see as satellites around something such as Milky Way. So again, on average, there are some scatter, but on average, the number of objects that have been destroyed through the cosmic time is a factor of 2 or so more than the number of objects that have survived and we see as satellites. And there are some other key points. I don't have time to bring the plots, but take my words for it. There are plots in various papers, including these ones and also mine. In terms of mass budget, even though there are more of smaller mass galaxies, in terms of mass budget, most of the mass budget is coming from the bigger objects. So the few bigger objects, if we look at the total mass of a stellar halo, the few bigger objects are dominating the mass budget. And because of dynamical friction, dark matter halos are extended. We have an object that is orbiting and being disrupted around an extended halo. It feels a drag force that we call the dynamical friction. Dynamical friction drags these bigger objects, slightly bigger. We are still talking about dwarf galaxies, by the way. These are just brighter side of dwarf galaxies. These are being dragged to the center. So when we look at the center-ish of stellar halos, they are dominated by very few, the mass budget is dominated by very few objects, and their orbits are relatively radialized. Again, there are various work that have shown that. So this is the general picture in CDM, that how the stellar halos are formed. And now we can kind of ask the kind of question of what happens if we change the nature of dark matter. For the same reason, some of these alternative dark matter, such as warm dark matter and SIDM, as Julia showed, show either the abundance or structure of dwarf galaxies. And they have been proposed to potentially address some of the small-scale tensions in lambda CDM. It's kind of obvious to ask, well, if they're changing the properties of dwarf galaxies, they can potentially change the properties of stellar halos. What I'm going to show, a lot of the work, basically all the work has been done by one of our former students who's currently a postdoc at Leiden, Victor Foruhar, and the master's student who's working with me. And most of the results I'm showing is already on arXiv if you want to check the details. Just to basically show you, I think you've seen these plots, so just a quick recap. I'm going to show some results related to warm dark matter. A recap that in warm dark matter, the abundance of a smaller, by the way, you're looking at the halo of a dark matter, Milky Way, sorry, dark matter halo of a Milky Way in CDM, lots of smaller structures around. When we look at warm dark matter, because the power spectrum is suppressed, fewer objects in warm dark matter. And if I switch to SIDM, as Julia was showing, the abundance doesn't change as much if you look at field objects. But if we look at the internal structure of, you can see it here, maybe by eye, you don't see that much of a difference. You can even by eye match some of the things on the right and left. So the abundances don't change as much. They change a little bit, I'll show you later. But the internal structure of objects can change. So I'm going to basically contrast the CDM scenario with warm dark matter and SIDM. If you're interested in the detail of the simulation, I can tell you more about later, but something to have in mind. I will show some results for Milky Way halos that are from a cosmological box that have been run, the same initial condition, the same galaxy formation model that have been run in CDM, SIDM, and warm dark matter. I will again contrast the properties of their stellar halos. And this is kind of a proof of concept study. Nobody had ever looked at the stellar halos in alternative dark matter. So I'm not going to tell you this is the answer. This is a constraint on warm dark matter SIDM, but the proof of concept, what can change if we change the nature of dark matter. First things first, we can look at the abundance of these destroyed objects that form the stellar halo. We can see the CDM in black,
And we can see warm dark matter has fewer objects. That kind of makes sense. There are fewer smaller objects in warm dark matter. Also, there are fewer of them here. Something that is perhaps wasn't very obvious to SIDM. Hopefully, the color contrast is clear. There is a blue line that is above CDM. So even though the abundance in the field doesn't change, because the internal structure of SIDM halos change, their subsequent evolution, their tidal disruption gets affected. So actually, they disrupt easier. That's why there are more SIDM subhalos that have been disrupted compared to CDM. So that's something to have in mind in terms of abundances. And then we can ask about the profile, the light profile or stellar mass profile of these stellar halos. For the dark matter, this is kind of, Julia talked about this, dark matter SIDM is flatter than CDM and warm dark matter. That's the dark matter profile. But if you look at the stellar halos, what we call the accreted stars from those accreted objects, we start to see also differences in the, actually warm dark matter CDM have very little difference. That's the red and black. Whereas in the SIDM, we see also a suppression of light or stellar mass in the inner region, which was very interesting. You can also see on average, sorry, it's here, I think, or here. There's a suppression of about like more than 50% when we go to SIDM, which is quite exciting. I guess I already said that warm dark matter is very similar to CDM, but the SIDM has shallower stellar profile in the center. The other very exciting thing that we also hadn't expected, but we found, is when we look at the kinematic features. So this is the beta anisotropy, this is the velocity anisotropy profile. I don't know if you remember from maybe undergraduate studies of dynamics. So the beta basically is telling you that if the beta is high, the orbits are very radial. If the beta is very little, the orbits are kind of quite circular. And we're contrasting warm dark matter and SIDM compared to CDM. Again, you can see the warm dark matter doesn't change as much, roughly compared to CDM. This is minus CDM. Whereas SIDM shows definitely orbits of stars that are more circularly biased. This is very exciting because with some of you who are familiar with Gaia, which is measuring the kinematics of stars around the solar neighborhood in the inner regions of the Milky Way, it can potentially give us some hints about the nature of dark matter depending on the orbits of these stars. Of Flash 1 results, because some of you, for those who are familiar with these plots, I don't have time to go to the details. We can look at kind of these sorts of plots are very easy to make these days with Gaia for the Milky Way. If you're familiar with Gaia Enceladus sausage, that's something like a Gaia Enceladus sausage that actually when we look at the SIDM, it disappears. Also, the energy of the orbits change from CDM to SIDM. So this is very exciting because of the new measurements that are available, and we should definitely look at the parameter space to see what we can constrain. And I leave you with the conclusion or takeaway points. If you don't remember anything from my talk, maybe the two takeaway points are the differences in the warm dark matter. Basically, if we go from CDM to warm dark matter, we see very, very little difference in the stellar halo properties. But if we change to SIDM, both the kinematics of the stars and also a stellar light essentially profile can change in SIDM, which can be used to constrain dark matter models. Thank you.
We have time for one question.
Thanks, Aziz. Wonderful talk. I just wanted to ask, these results are when we don't have feedback in SIDM simulation, right?
So this is a full hydrodynamic simulation. So this is completely, it has everything.
And the cross-section, I missed that slide.
Right, yeah, I didn't go over the details. So the cross-section is constant 10 centimeters square per gram. So technically, this is on the scale of Milky Way. It's almost ruled out. So this is at the boundary of what is acceptable. But as I said, this is more of a proof of concept. So we kept it as some sort of basically a little bit extreme. It's not very extreme, but it's at the edge of what is acceptable for Milky Way, just to see if any differences are shown. Now that we see there are differences, now we should look at definitely different SIDM models to see what we can constrain.
So thank you again. So now we have Francesca Francodi talking about probing dark matter in the bar dynamics.
Okay, let's see if I manage
manage with these clickers and whatnot. Okay, so let's see if we can make this movie play. Oops. I clicked too soon. Yay. Okay, great. Good. So thanks a lot to the organizers for giving me the opportunity to tell you a little bit about some of the work we've been doing in using the dynamics of galactic bars in order to probe dark matter, in particular probe how much dark matter there is in Milky Way-like galaxies. And if I have time at the end, I might show one quick slide about also what we can do to probe the nature of dark matter, as Julia was mentioning before. So just to put everyone on the same page, bars are these rotating, or it was rotating, it's stopped rotating now, these rotating objects that we see in, see if we can, there we go, that we see in many spiral galaxies running through the centers of spiral galaxies. And these bars, they are made up of resonant orbits, which you can see in this video here. And these resonant orbits in the frame rotating with the bar, they essentially move up and down the bar. So this is the stars that are on these resonant orbits, and these are stellar rotating structures that we see in many spiral galaxies. As I was just saying, yeah, we see these in a large fraction of the spiral galaxy population. So 2/3 of disk galaxies in the local universe have these bars, so they're very common, including our own Milky Way is also a barred galaxy. And if we look at the fraction of bars, so how this changes in time, as I was just saying, the bar fraction is quite high at low redshifts. It decreases as a function of redshift. This is shown by studies using HST, and more recently also with data from JWST. We've been finding that actually at redshifts of about 1.5, we already have about 20% of galaxies hosting bars. So these are, the fraction decreases, but there's already a quite substantial fraction of disk galaxies that host these bars already at redshifts of 1.5. Okay, so why am I talking about bars in a dark matter session? The reason for that is that bars and dark matter halos are tightly linked. And they're linked in a number of ways, and I'm just going to highlight two here. So the first one is that the formation of bars is tightly linked to how much dark matter there is in galaxies. And this was shown already with this seminal paper by Ostreicher and Peebles in 1973, who showed that if you take a disk galaxy and you embed it in a massive dark matter halo, you can stabilize the disk against forming a bar. The other way that bars and dark matter are very linked is in the pattern speed of bars, so how quickly they rotate. If a disk galaxy manages to form a bar, but it's embedded inside a massive dark matter halo, then the dark matter can actually slow down the rotation of the bar through dynamical friction. So you can think of your bar as kind of rotating inside this dark matter fluid that's exerting a kind of frictional or drag force on this rotating bar. Okay, so I'm going to be touching a little bit on both of these points and tell you about some of the results that we've been getting and what this is telling us about how much dark matter there is in massive spiral galaxies. So in the first part, in both of these, I'm going to be talking about results that we've been getting by using the IAU GA cosmological simulations and comparing these to other simulations and observations. So just a few quick words. So the IAU GA simulations are a suite of over 30 high-resolution hydro-cosmological zoom-in simulations. These have a comprehensive galaxy formation model with star formation, stellar feedback, AGN feedback, and these have formed galaxies at redshift 0 in the range of the Milky Way. So they have halos in the range of the mass of the Milky Way. But we've also extended these to higher and lower masses as well. And in these simulations, you can follow, of course, the dark matter, the gas, and the stars all at the same time. Okay, so one thing that I wanted to focus on is on the baryon dominance of these galaxies in IAU GA. And in particular, looking at this in the plane of the stellar mass versus halo mass. And what you can see already here by eye, so the red points are the barred Auriga galaxies, and the blue points are the unbarred Auriga galaxies. And what you can already probably see here is that the barred galaxies tend to lie above the unbarred galaxies. So that means that for a given halo mass, your barred galaxies are more have higher stellar masses than the unbarred galaxies. And we can quantify this a little bit. So we did this here by taking the offset of each of these galaxies from the average abundance matching relation, which is shown here in blue. This is the relation by Moster et al. And you can see that barred galaxies are on average have a 2 sigma offset from the abundance matching relation, whereas the unbarred galaxies are much closer to the abundance matching relation. And if we look at the kind of baryon dominance, so this is the contribution to the rotation curve from the stellar component over the total. So you divide the stellar component over the total. You can see that for the barred galaxies, that's shown in red, these are more baryon dominated everywhere as compared to the unbarred galaxies. But one interesting thing to highlight is that this black line here shows you the model for the Milky Way from the work of Bovy in 2013. So this is a very commonly used model for the Milky Way 14. And you can see that according to dynamical modeling, it looks like the Milky Way is actually even more baryon dominated than what most cosmological simulations are showing today. And this is, as I'll show you in a bit, this holds true for many simulations. It's not just for Auriga. But yeah, the key takeaway is that barred galaxies are more baryon dominated than unbarred galaxies in these cosmological simulations. Now, this has an interesting consequence on the Tully-Fisher relation. So we heard a lot about the Tully-Fisher relation a couple of days ago from Federico. So what I'm showing here is the stellar Tully-Fisher relation. So this is log of stellar mass versus log of the kind of V flat. And the Auriga galaxies, they form a tight relation, very little intrinsic scatter, compatible with what we see in observations. But the interesting thing to see here is on the right here, where you can see that you can fit a relation to the barred population, which is the red line. And this is a different relation than the one for the unbarred galaxies, which is the blue line. So the Tully-Fisher relation for the barred galaxies is offset from the one from the unbarred population. So for a given kind of V flat, you have more stellar mass on average in the barred galaxies. Now, this is really important. If such a thing were to be detected, this would rule out something like modified Newtonian dynamics or MOND, because as we were hearing the other day from Federico, in a Mondian framework, there is zero intrinsic scatter in this relation. It does not depend on the intrinsic on the internal properties like morphology and so forth. So that would be a really interesting thing if we can detect any kind of thing like this in large samples that are coming soon. In the last couple of minutes, I just wanted to talk about the bar slowdown and dark matter. So as I was saying, bars, they rotate and they have a given angular frequency called the pattern speed. And if we look at the rotation, the angular frequency of stars in the disk, which is decreasing, there's a given radius at which stars in the disk corrotate with the bar, and that's called the corrotation radius. Now, if we have a lot of dynamical friction and the bar slows down, then this corrotation radius will move outwards. So when the bar pattern speed decreases, the corrotation radius increases, but dynamical friction doesn't affect the bar length. So basically, if you have a lot of dynamical friction, what happens is that the ratio of the corrotation radius to your bar length will increase. And you can try and measure this in order to see how much dynamical friction there is in galaxies. Now, people usually do this by looking at this kind of plane. This is corrotation radius versus bar length, and everything down here is considered fast below this ratio of 1.4, and everything above here is usually labeled as slow. And this is where the observations lie. So observations tend to find that there's not a lot of dynamical friction in galaxies. But most kind of cosmological simulations, big box cosmological simulations, for example, Eagle, Illustris, and TNG, when they've gone and done this kind of exercise with barred galaxies, they tend to find that bars are very slow and incompatible with observations. And this has raised the question, are fast bars incompatible with lambda CDM? So we went and looked at this in the IAU GA simulations, this cosmological zoom simulations, and this is what we found. So as you can see, IAU GA, overlaps nicely with the observations. So bars in IAU GA are fast, and they're actually in agreement with observations. So this, of course, raised the question: why are IAU GA bars faster than in other cosmological simulations? Since IAU GA is also carried out in the Lambda CDM framework as well. So we looked at a few different things. I don't have time to go through it, but essentially what we found is that the baryon dominance of the IAU GA galaxies is higher, which is the red color here, as compared to that of illustrious and Eagle simulations. So IAU GA galaxies are more baryon dominated. And this is an interesting consequence that if we look at something like this F-star planes, which is the stellar mass over the baryon fraction times the halo mass, this means versus the stellar mass, so we see that IAU GA also lies above the relations for illustrious and Eagle, which are shown in green and in purple. But this is compatible with actually the spark sample. And we heard a little bit about this also a couple of days ago by Enrico and by Mike Fall about this nice work from Lorenzo Posti that showed that massive spiral galaxies are offset from the abundance matching relation in this F-star, M-star plane. So in IAU GA, we find the same kind of trend as well. But what we're seeing is that barred galaxies actually should be baryon dominated in cosmological simulations in order to have their dynamics consistent with observed bars. If they're not, then you don't get the correct kind of properties for bars. So dynamics of stellar disks and bars can really constrain galaxy formation models. And what we're seeing is that most cosmological simulations produce undermassive stellar disks, which is telling us that the feedback that we're putting in is too strong. And just maybe in the last couple of seconds, I'll just say that we are, as Julia hinted at, we are currently also probing the nature of dark matter with bars as well. So we are running these new simulations called IAU GA Superstars and IAU GA Superdarks, which will also have self-interacting dark matter in order to try and probe the nature of dark matter, which we've heard can be different in the inner regions of halos, which is exactly where the dynamics of bars are useful for probing these kinds of things. So I'll leave you with my take-home messages.
Thank you very much. So one question.
Very nice talk, Francesca. So as you know, the abundance matching relations are constructed in order to reproduce the stellar mass function of galaxies and make it compatible with the halo mass function, which is a power law versus a Schechter. So, I appreciate that to solve these problems of fast bars and other things, you need galaxies to deviate from the average abundance matching relation. But then isn't there the risk that the statistical population of these galaxies with bars or no bars will have completely wrong abundances? And so cosmologically, it wouldn't make sense anymore in a Lambda CDM context.
Well, I think this was what was addressed by Mike the other day, right? That if the early type galaxies might have much lower, might fall much further below the M-star M-halo relation, and so because of this high mass N, you have a lot of these early types. So then the average relation is still maintained, even though your spirals are going up and the early types are below.
Yeah, I know that. But if you look at the stellar mass function just of late type galaxies, that is also Schechter, right? So one would need a very contrived model in which the halo mass function that hosts only late type galaxies is a Schechter too, rather than being a power law, right? I mean, there is a scale that should happen in both, where there is the knee of the Schechter function. But we can discuss this later.
We can discuss it.
Okay, so thank you, Francesca. So now we have difficult to pronounce Presmec-Ross. It is already so about the constraint on the primordial black hole as dark matter from the 20 years Ogle observation by co-lensing to LMC. Is it possible to have the... Yes.
Okay, excellent. I'm Przemek Mills. I'm an assistant professor at the University of Warsaw. So this question, is dark matter made of black holes, was brought again to life a few years ago with the discoveries of gravitational waves from merging black holes by LIGO and Virgo. I think that most of you have seen this plot, which shows the distribution of masses of known neutron stars and black holes. And what is really striking in this picture is that the black holes detected by LIGO and Virgo are, on average, several times more massive than those black holes that we knew before in our Milky Way with traditional electromagnetic observations. So, and there is a lot of discussion why this is the case. And one of the ideas that was put forward soon after the LIGO and Virgo discoveries was that LIGO and Virgo detected primordial black holes, which may have formed in the very early universe. And those black holes may comprise a significant fraction, if not all, of dark matter. I think some of you may think this idea is outlandish, but those papers that proposed this idea have been cited, have accumulated over 1,000 citations as of now. And actually, if you look at the papers that contain the phrase primordial black hole in the abstract, there's at least one paper daily published on that. So there is a lot of interest in this idea, at least in some communities. So how to check if this idea is correct? We know that large amounts of dark matter are located in our own Milky Way. So if it were composed of black holes, we should see a lot of gravitational microlensing events caused by those black holes in our Milky Way halo. Microlensing is an effect predicted by Einstein's theory of general relativity, which basically says that the light can be bent and magnified by the gravity. So suppose that you have three objects observed on Earth, a distant source of light, which may be located in the Large Magellanic Cloud, and you have a third body called the lens, located almost exactly between the observer and the source of light. The gravity of the lens will cause the light from the source star to be magnified, at least temporarily. And what we expect to see is to observe a transient brightening of an otherwise constant star, which we call these brightenings gravitational microlensing events. Here we have an example light curve, the brightness as a function of the time. If you think about microlensing events toward the Large Magellanic Cloud, with sources in the LMC and lenses located in the Milky Way dark matter halo, the timescales of these events are about 60 days for solar mass stars. However, the larger the mass of the lensing body, we expect longer microlensing events. Of course, this idea to use gravitational microlensing is not new. In the past, I would say 2 decades, microlensing experiments have ruled out compact objects in the very broad range of masses from 10 to minus 10 up to about 10 solar masses as a dominant component of dark matter. But as you can see, those previous experiments weren't really sensitive to masses of 10, 100, 1,000 solar masses. So exactly masses of black holes that have been detected by LIGO and Virgo. And this is why people started to explore this idea that maybe such massive black holes may form dark matter. But fortunately for us, there is one experiment that has been observing the sky long enough to be able to see such very long timescale microlensing events by massive black holes if they existed. And this experiment is OGLE. It's been run by astronomers from the University of Warsaw for the past 30 years. And in particular, some of our fields toward the Magellanic Clouds were observed since late 1990s. So we have more than 20 years of time series photometric data to see if we can find long timescale microlensing events that would point to massive black holes in the Milky Way halo. And this is the work I've been doing. So about 55 million stars located in the LMC, in the regions of the LMC, were observed for about 20 years by AUGL, and the remaining 25 million stars in these outer regions of the LMC had only 11 years of data. Of course, this is long enough to try to detect those very long duration microlensing events that we would see. So we analyzed about 80 million light curves of stars located in the Large Magellanic Cloud. As I said, most of these stars had 20-year long data. In that huge data set, I was able to find 16 microlensing events, all of which are shorter than 200 days. Here you can see a couple of example light curves, but we think that all of these 16 microlensing events can be explained by stars and brown dwarfs either in the LMC itself or in the Milky Way disk. So there is no need to explain those 16 events by black hole dark matter. We also run very extensive simulations to calculate our sensitivity to those long timescale events that we could potentially see. Here you can see this detection efficiency. Oops. Here you can see these detection efficiency curves as a function of the event timescale. So in principle, we could find events that have timescales of 8 to 10 years. So we would find them if there were any in the Milky Way halo. And by combining the model of the Milky Way halo and our simulations, we could calculate how many events are expected if the entire dark matter was composed of objects of a certain mass. So for 100 solar mass black holes, we expected to find over 100, perhaps a few hundred microlensing events in our dataset. But we only found only 16. So we are able to translate those numbers into limits on the amount of dark matter in the form of compact objects. These are these red regions. So here on the x-axis, you have the mass of the compact object. On the y-axis, you have the maximum fraction of dark matter that can be made of it. So these shaded regions are excluded by our data. Less than 1% of dark matter is composed of 10 solar mass objects. Less than 3% is composed of 100 solar mass objects, and less than 10% is composed of 1,000 solar mass objects. These limits are more than order of magnitude stronger than what we had previously, and they also extend to much higher masses. Perhaps some of you may have heard that in the past few years, microlensing surveys have detected an excess of short timescale microlensing events toward the galactic center, in the galactic bulge. And generally, the idea is that these events are because of planets, free-floating planets without any star, or perhaps planets on wide orbits around these stars. They seem to be quite common, but there was a paper back in 2019 suggesting that maybe these are not planets, but planetary mass primordial black holes that can form from 1% to 10% of all dark matter. That paper has 300 citations as of now. So we wanted to check that idea. Of course, if we see planetary mass primordial black holes toward the galactic center, we should also see them in the direction of the Large Magellanic Cloud. So in the past 3 years, we carried out a high cadence survey of the Magellanic Clouds to try to see if we find very short duration microlensing events there. The long story short is that we didn't find any. So again, we were able to put very strong limits on planetary mass primordial black holes in this planetary mass range from 10 to minus 9 up to 10 to minus 3 solar masses. And that's my summary. I will leave it here. Thank you.
Nice talk. I have a comment. I think there is another argument pointing out the difficulty to have dark matter made by black holes, because we should have a lot of Bondi accretion. So if we have millions of black holes moving in the gaseous atmospheres of clusters and galaxies, we should observe a lot of X-ray emission that we do not observe. So I think this is quite a strong argument.
Of course, gravitational microlensing is just one of the ways of trying to find these. You're right that you can also try to do. It's an additional argument, but it's more complex because it involves physics of accretion, which is more complex. So it's not. Whereas for microlensing, it's just geometry. So it's much easier than accretion.
Thanks for the talk. I have two probably very naive questions. So if you have a primordial black hole with the mass of 10 to the 3 to 10 to the 4, say, solar masses, wouldn't that change like dynamical passes of stars? Can't we like explore that with Gaia so we don't need that long exposure time?
Yes, it can. Especially it may change the dynamics of stars in dwarf galaxies, which contain a little number of stars and a lot of dark matter. So I think there are some also limits on those very massive black holes from the stability of dwarf galaxies.
All right, thank you. And also, I don't know if there are simulations for the whole dark matter being black holes, but generally, how does a galaxy, say, halo function, like density function would change if your dark matter is not something diffuse? It's clump.
I don't know.
Okay, thank you.
Thank you very much. So now we have Connor Bottrell talking about from optical imaging to dark matter halo through simulations.
Interesting. Yeah, okay. Right. So, okay, thanks. So we heard earlier in the week, we also heard a very nice talk from Francesca laying out this picture that galaxies and the high mass end of the halo mass function, there's this dichotomy between early type galaxies and late type galaxies in terms of the stellar mass to halo mass relation. Now, this is because the physical histories of these galaxies are different, right? And so what I'm going to do in this talk is I'm going to talk about how this morphological dependence on the stellar mass to halo mass relation can actually be extended to much lower halo masses, and how morphologies of galaxies can be exploited to offer constraints on the halo masses of galaxies. All right, so a acute, albeit perhaps not terribly physical, description or explanation of the intrinsic scatter in the stellar mass to halo mass relation can be arrived at just from sort of mass ranking. So if we start with the halo mass function, oops, wrong one. If we start with the halo mass function here and the stellar mass function here, and we just assume that these things know nothing about each other, okay? And so then we can take a narrow window in stellar mass, this little narrow window here, and prescribe statistically sample from this corresponding window in halo mass and sample from this corresponding window in stellar mass just into those halos and populate those halos, then we arrive at some ratio, like some scatter in stellar mass for a fixed window in halo mass. Now, if we can do this at the high mass end, we find that that scatter for stellar mass at fixed halo mass is relatively low. And so this explains why the scatter in the stellar mass to halo mass relation at the large halo masses is low. Whereas if we do this at low halo masses, where the stellar mass function flattens, then we find that the scatter is relatively large, and the galaxies that we need to draw from to populate those halos are different, right? And so this means, as I said, it's not a terribly physical picture, but it is a cute one. And so now let's get into a little bit of the physical scenario. Well, it's just, if you think about it, at fixed halo mass, the difference in stellar mass just comes from whether a galaxy and its progenitors were more efficient at converting their gas into stars or not. So that just arrives at whether you have more stars at fixed halo mass or less stars at fixed halo mass. And this is dictated by the physical history and the assembly histories of galaxies. A galaxy whose assembly history is dominated by the smooth accretion of gas, or the smooth assembly of stellar material from gas, is going to have a very different morphology and corresponding stellar mass to halo mass relation, or stellar mass to halo mass ratio, compared to a galaxy at the same halo mass whose assembly history was dominated by events which either accelerated or interrupted its star formation efficiency. And so the morphologies also encode these physical and assembly histories. So we can potentially exploit the morphologies of galaxies to make more accurate predictions of halo mass at fixed stellar mass. And so this is what we did. Oops. Okay, no spoilers. Okay, good. So we constructed a sample of galaxies from using the TNG 50 simulation to examine this relationship between morphology and stellar mass to halo mass, stellar mass to halo mass ratios. So here are a bunch of galaxies from TNG 50, which I constructed MOCs these are just GRI bands from radiative transfer post-processing. So these include dust and all of the various observational filters. And so we can go one step further, and we can insert these MOCs into real imaging fields such that they incorporate all of the systematics that affect measurements for real galaxies in the real universe by real observational tools. So things like, measuring the Sirsic properties, measuring concentration, asymmetry, and smoothness, Gini, M20, all these structural parameters that describe the morphology of galaxies. But also for these galaxies, the beauty is that we have access to their halo masses and stellar masses. And so we can train a model, and this is what we did, a simulation-based inference model that connects the morphologies of galaxies to stellar mass and halo mass predictions. So morphologies, and what we estimate from the model is stellar mass and halo mass simultaneously. So we don't make this easy for the model. We're not giving it stellar mass and then asking it just to assign a particular halo mass. We're making it predict stellar mass and halo mass simultaneously. And before I get into the results, we measured the morphologies of these galaxies using basically standard tools. And what I want to highlight is that there is much more information that is available in these images that can be exploited, right? And so Jiani Chu, who is going to be talking in the next session, so you don't have to wait too long to know what the difference is going to show you how using all of the information in these maps, using a model which actually has a visual cortex, or sorry, something like a visual cortex, can achieve much higher accuracy. Okay. All right, so here we have the predictions from the model. So we give the model things like the magnitudes and morphologies of galaxies, and we ask it to predict stellar mass and halo mass. So, oops, back. Yeah, so here we have the inferred stellar mass as a function of true stellar mass, and inferred halo mass as a function of true halo mass. And so if what you see is that this model is able to predict, what we found is that the model is able to predict stellar masses and halo masses, or at least, sorry, just predict halo masses with 40% greater accuracy than what can be inferred if you just assume the true stellar mass and use the scatter and the stellar to halo mass relation to infer halo mass. So what this means is that 40% of the scatter in the stellar to mass to halo mass relation is encoded in galaxy morphologies. Okay. So that's pretty powerful, very useful. The other thing that's very useful about this model is because it is an Bayesian framework, we're able to produce posteriors from this model, posterior samples, from which we can infer uncertainties. So in combination with additional constraints on halo mass that maybe aren't terribly constraining, suppose you have a survey which is not totally spectroscopically complete, but nonetheless gives you some satellites within a group. This would give you a corresponding halo mass and an uncertainty from the dynamics of those satellites for that central galaxy. This tells you that you can exploit the morphology of the central to offer additional constraints and produce a joint posterior for those two posteriors. And so we're just showing here the predicted halo mass and predicted halo mass for a field galaxy and a group central. And where this is the dashed line is the true halo mass, and the black is showing you what you would infer. It's the intrinsic scatter and the stellar mass to halo mass relation at fixed stellar mass, for the true stellar mass of the galaxy, except we're not giving it the true stellar mass, we're inferring it. So all this is to say is that the morphologies encode a significant amount of information about the halo. And you can exploit this relationship to make more constraining predictions of halo mass. And we constructed this just a little bit of advertising, we constructed this very large public sample of realistic MOCs, about 1 million MOCs from galaxies from the TNG 50 simulation, as inserted into the HyperSubPrimeCam Super Strategic Program. And we've constructed these for Eagle and Simba, and you can pay attention, those will be available soon. Thank you very much.
Thank you. So we have time for a few questions.
Very, very interesting talk. I'm wondering if you tried to maybe assess the effects of the kind of the subgrid physics by, for example, using your model, but on a different suite of simulations to see how well that performed.
That's almost like a plant question, because it's as good as a plant. So the first experiment that we want to do before we can apply this to observe real galaxies in HyperSubPrimeCam is to apply this model in a simulation to simulation comparison. So a universe to universe comparison for which the subgrid physics are different. Yeah, so absolutely, this is part of our plan. The next step in the plan is to apply this to real galaxies for which we have known halo masses from very good constraints from satellite kinematics and in samples like Gamma and Devils and forthcoming surveys like WAVES.
How much of a redshift range were you including in these MOCs? Was it very local, or were you extending the sort of implied redshift range and recovery of that sort of from your morphology as well?
That's a very good question. So our training set was set to redshift 0.1, and our test set was also at redshift 0.1. So we're not exploring a very broad redshift range at all. Instead, what we plan to do is we plan to have a different model which is prescribed to each various bins in redshift. Because having a model which is able to handle the differences in structural parameters that you get just because of surface brightness dimming would be challenging. So we're just going to train different models for each set, which will have different corresponding uncertainties.
Okay, so thank you very much. Now we have two short talks without time for questions, but you can ask them in Slack. So we have Surajit Kalita about the fast radio burst to probe the primordial black hole as dark matter.
So hello everyone, I'm Surajit. I'm a postdoc at University of Cape Town, and in this short talk, I'll just give a glimpse of how fast radio bursts can be used as a probe to constrain primordial mass black holes made of dark matter. And this work I have done with Amanda Weltman and Shruti. So I'm not going to in details, but fast radio bursts are very interesting objects. They're radio transient events, very bright in the sky. And because of one of the main properties, which is basically called dispersion measures, they have very high dispersion measures. Almost you can see in this plot. Oops. So you can see in this plot, it's almost going up to 3,000 parsec per centimeter cube, which corresponds to a redshift of around 3. So these are very good astronomical probes, which can probe cosmology, one of them. And generally, the dispersion measures has 3 or 4 components. One is like Milky Way and its halo coming from its halo. Another is coming from its host host galaxy and the intergalactic medium. And that intergalactic medium is very much dependent on the underlying cosmology and the other fundamental parameters. So I'm just using this last equation, and I'm not going in detail, but I'm using a modified gravity metric, which looks like a little bit of Schwarzschild plus additional term. And I'm using one particular phenomena, that lensing that you have come across. Suppose there is an FRB originated at points that source, and it's coming to observe to us, and in between there is a black hole which has some dark matter, and you see multiple images of that. So we see some gravitational lensing, but no lensing of FRB has been confirmed yet. There are few speculations, but if it's not confirmed, then we obtain the fraction of primordial mass black holes made of dark matter in that formula. And you can see with respect to different modified gravity parameter, we obtained on the right-hand side the different mass fractions. And if we just compare this with one of the previously reported results from again from FRBs, but with plasma lensing, that means plasma is there in the intervening medium. They are very similar. The plots look a little bit different because of the statistics we used in both the papers. But effectively, it's constrained a mass range of around 10⁻⁴ to 10⁴ solar mass black holes. And so this is my key takeaways, that FRB lensing can help in constraining fraction of dark matter. And this result will be very much improved by HIREX, which is being planned in South Africa, which will detect many more FRBs in our southern sky. And of course, the main key takeaway is that modified gravity mimics like a scattering screen in the path of the light ray. And this is our published paper. You may look at it for more details. Thank you.
So the next short talk is Victor Robles, about supernova feedback in dwarf galaxies and the FDM, fuzzy dark matter.
Thanks. Okay, so I'm Victor Robles from Rensselaer Polytech Institute. This is in Albany, in USA. So the first thing is, before I start my talk, I just want to do a little bit of advertising. So I'll be hiring a postdoc from the next year, but it will be advertised next fall. So if you're in the job market, please let me know. Okay, now back to the talk. So I guess like we heard about a little bit of fuzzy dark matter at the beginning, but I just put this so that everybody is kind of aware of what it is. So essentially the key features are that you have, instead of having like a WIMP or like very high mass particle, you're going to assume that the dark matter is a very tiny object. And if you do this, then the Rayleigh wavelength for this will be very large. So in fact, it's a kiloparsec scale. So what this actually implies is that you're going to have some sort of like quantum behavior on large scales. And then what I'm showing here on your right, it's actually a projected density of a dark matter halo in this model. And what you can see here is a very different distribution that's compared to CDM or SIDM even. So you see that there's a lot of clumps. So unfortunately, I don't have a movie, but essentially what you're going to find is that there's a very compact object at the center, which is called the soliton. And you can see the density profile on your left. So this is usually a very generic feature of this model. And then on the outskirts, you're going to see all these sort of density fluctuations that are going around, and they are time dependent and spatially dependent. So let's see. Okay, I guess it's see the red one? Okay. Green. I don't see green, but okay. All right, thanks. Sorry. All right, so what we've been doing is basically running simulations of this, and then one of the things that we've been doing, especially this is kind of work by one of the postdocs now at the Premier Institute, so it's Luna Sagarak. And so basically what we found is that, what we did essentially is to run one of these isolated systems, but we kind of tried to mimic the feedback effects. So this is more like a net effect rather than the specifics of feedback. So what we basically is, you can think of this as a semi-analytical model in which basically what is shown there, very weirdly with these arrows, but the point is that basically we started like accreting some gas at the center of the dark matter halo or at the center of the soliton. And then there's a time in which we basically reach the maximum of this mass accreted. Then we'll let the system relax, and then we just blow out all the gas, which is shown by this, setting the potential to zero. So this is a very bursty effect. And then we kind of explore what will be the effects on the dark matter physics for this particular model. And what is shown at the bottom is basically our initial condition. We start with a soliton. And then once we have like the blowout, basically you see that there are some sort of oscillations in the density. This is in the central density. But when you look at the dark matter distribution of the whole system, you see that there is still some oscillations. Basically, you can think of these as expanding, contracting, expanding, contracting. So this is actually interesting because in none of the other models, you will see that this is a continuous effect. So you will see that there's some effect and then it just fades out.
So the important point of all this, I guess like the key message is that if you compute the circular velocities of these dark matter distributions, what you find essentially, you can just guide your eyes to the shaded regions. So this is the post-burst phase. And effectively what you see is that depending on how big the burst of supernova feedback is, you will see a little bit more or less scattered. But in all of these cases, what we found is that due to these oscillations of the central density potential, you will see that at any given time, this is the range in which you can find your halo at. So this is not something like, you see your halo and then because it's been there for many giga years, you expect to see some sort of unique density profile. This is in fact, any of these are possible. So what this is actually, what is important about this is that if you put your local group dwarf galaxy data, specifically the ones that are not in the Milky Way and the Virial Radius or Andromeda, is like in between. So these are isolated systems. So what we find is that they all lie within the scatter of this system. So this is pretty good because we don't really have to do any sort of fine tuning with the feedback models. And in fact, we could just recover some of the scatter if the dark matter is of this type of nature. So thank you.
So please also applause all the speakers of the session. Now the cafe pause, we come back in half an hour.
Already tripping myself.
You're back to astronomer chic.
Astronomer chic. What's that?
It's great.
Oh. Sharing in my sweatshirt. Astronomer chic. Oops. Hey, hang on.
Hello? Ah, yeah, it's on. Okay, good afternoon, everyone. We'll resume promptly and we'll try to stay on time because I have been instructed to keep the session on time because we've got the closing ceremony shortly after the end of this session. So without further ado, I'd like to introduce our first speaker for today, for this afternoon. It's Françoise Combe, who's going to be giving an invited talk about the alternatives to CDM, MOND, or axion-like particles. If we could have the slides, please. I'll give you a 5-minute warning.
Thank you. Okay, so I will speak today about two alternatives. First is a modified gravity. Oh, okay. I've not touched anything. First is a modified gravity, and the second is action-like particles, where you see already some simulation about that. So first, it doesn't move. Yes. So first, MOND, as you see here, it's 40 years ago because Milgram has proposed this hypothesis in 1983. That's why we celebrate this birthday last year in a meeting in June 2023 in St. Andrews. It was really lively. Well, what are the issue that I will try to cover here is first, you have this I will put the laser. Yeah, first we have these, which are successes of the MOND. That means the good fit of rotation curves, the Fisheration. We have learned a lot about that this session. Then you have some issues that were debated a lot and were problems, but are in path to be solved. I will just describe them. And then there are big problems. There are still mysteries and remaining problems that are not solved. So first, for this is there scalar tensor theory? As you know, there was a first step in by Jacob Bekenstein in 2004 that wanted to have a covariant theory, a T-BES, a tensor vector scalar. And this vector was a unit time-like vector to compute the gravitational lenses. There was two problems in this T-BES. The first was that the velocity, the speed of the gravitational waves were not equal to the speed of light. And also there was problem in the anisotropy of the CMB and the mass spectrum. So with this new theory, ether means that they keep the unit time-like. This unit time-like vector means that it is an Einstein ether theory. So you have this vector, the scalar and tensor again, but with different functions. And then, as you see, they can fit perfectly the CMB, the anisotropies of CMB. In fact, as soon as we have variance, you have a scalar field that treats that. And then, of course, you can have several shapes. They have some different residuals, but in fact, there is still some freedom. But also, they fit the mass spectrum of the galaxies. So all the early universe will be solved this. Although there is a recent work by Verbeyen and al. That they tried to resolve this equation analytically. It's quite complex, so it is in spherical geometry. And in this geometry, they find that it is quite good until the end, where there is some oscillation behavior. So we have to still work on that, and also make simulation to simulate disks, which are not able to do with analytics. So maybe it's in paths to be solved, but there is still some work to do. About wide binaries, it has been debated a lot. Yeah, there is two groups, Shea 2024 and before, and Hernandez et al. They found that when you have a wide binaries of stars, and you are away that the acceleration is lower than the critical acceleration that 10 to the minus 10 in SI units, then you have a problem. These people, Picardis and Sutherland, and also Bannick et al., they all took, in fact, binaries from Gaia. So you have thousands of binaries, but you have to take pure binaries because there are some with tertiary, some are projection effect, and so on. So you have to take pure binaries. And these people take also those who are lower than 2000 AU, where you have a Newtonian dynamics, you have not only Mond dynamics. And what they discovered is when there is some noise in this analysis, because you can have inclination effect that you don't know because you have elliptical orbits, so it's degenerate. And all these errors mean that even in the Newton regime, you have an acceleration which is lower than predicted. So you have to calibrate that, and that noise systematic effect. So they calibrate, and here you have the RAR, that what we have talked this session, the radial acceleration relation. Here you have the acceleration Newtonian, and you see that when you are Newton in lower than 2000 AU, then you have indeed the same kind of thing, and the red is for the wide binaries. And you see that indeed they are above Newton, but of course the others were only saying 7 to 20 KU, so only Mond regime, and they had not calibrated on the Newtonian regime, okay? So that's why they found different things. Well, this means that it is not, the truth is still out, and we have to work more on this, but it is still not a problem, apparently. Then you have a solar system also, because 10 years ago, there was some papers here saying that even the precession of Saturn and the ephemeris of Saturn were not corresponding to what you expect in the GR. And there was, of course, it's very, very tiny. You are almost in the Newton regime and in the solar system, but you can still have very small things. And but recently, the Fianga et al. Paper, those people that in celestial mechanics that make the models of the ephemerides, they say that they have plenty of parameters to fit, and they fit that within a model, within a GR. So within a GR, you have to fit all the models, which are the masses of the planets, of course, but also the initial conditions, maybe also the flattening of things, for instance, the flattening of the sun. They fit that to fit the past history of the planets with GR. So they say that you have to redo everything with another model. Maybe with another model, modified gravity, you will find less residual for the past, and then you have to model for the future. So finally, this might not be a problem. Okay. So I also just present you some of the recent work. You see all the 2024 that has been done on this related to Mond, in fact. And here you have these hooks that were 2 days ago discussed a bit. Here you have some Phi2, so lambda CDM simulations, where they say that they see also the RAR, the radial acceleration, the observed one, and the Newtonian one. And of course, they can also simulate that, but they have hooks in this, if for a galaxy, you have something which you have two values for one observed. Why? Because you have a core in the dark matter, and the core is due to the feedback and so on, and you can have hooks. So they claim that if you find hooks in this RR, you could distinguish between Mond and and CDM. So it's a nice idea. But for the moment, it is the hooks are within the error bars, unfortunately, so you cannot decide, but it will be interesting. They also say that at the end, in the weak regime, you should have a band because you have a saturation with the FB, the universal barrier fraction, that you will not have in MOND. So at least you have some ways. If you have more precision, you have some ways to distinguish between two theories. That is very interesting. Well, you have Yapan and Krupa that have simulate relic galaxies. These relic galaxies are very old ones, quenched, and they are in clusters. So they have not fueled by gas. That's why they are relic galaxies. And since it is in a cluster, and I told you that in clusters, MOND doesn't work at all, they have added some neutrinos and HBM, and they claim that they find also this relics, that is star formation rate is corresponding to the observation. And also another interesting work by my view that makes some collision, head-on collisions, like to form a ring, like the cartwheel that we know very well. And they say that since you have an external field effect in MOND, that is, when you have two big galaxies, the acceleration of one is destroying the MOND effect. So you have different physics in the two. So it's a way, if we can work on these collisional ring galaxies, it's a way to distinguish between the two. So it's very interesting. Well, now I come to the problems. Also in galaxy clusters, you know, there is a big problem not solved, that's for MOND, that the acceleration is not low enough to have all the MOND boost. Here, there is not only the problem I just told, it's a global for the cluster, but for galaxies in cluster also, and that's a work by Jonathan van Lisch here and collaborators, that they took some UDG, ultra diffuse galaxies in the Coma cluster, and you see, well, they are not all very precise in their sigma. You have sigma because there is no H1, you have no rotation curve, but you have a velocity dispersion of the stars. So in some cases, they are precise. In some, you see the error bars the gray is quite big, but they all, surprisingly, they all fit with, of course, error bars. You see that they're very high. They all fit the RR, but they should not, in fact, because you are in a cluster where you have an external field effect. So we are surprised that it works so well. It should not work. So that is a problem. So it's still another problem in clusters. Okay. Then to solve this problem, there is two solutions. Either, and Nagesh et al. Tried to find these two solutions. Either there are tidal tails in clusters, of course, they are in an interaction, and since the tidal tails are not in equilibrium, they could have a higher dispersion because of that. So is it that? They conclude no, it's not enough. But there is a second explanation, is that when this UDG enters the cluster, it keeps the velocity it had in MOND regime, and has a time to relax to the new regime with an external field effect. And this can take something like 8 gigayears. So maybe all these are there because they have not time to relax in the EFP regime. So maybe it's not a problem, but it has to be worked out a little bit more. There are also in groups, UDG. Some have been like this very famous one, like Dragonfly 44. They have been well destroyed by MOND, in fact. And well, there is, we must say that there is a lot of freedom because you have the anisotropy. There is no gas there, so you have the anisotropy of stars, the radial stars, and so on. So within these error bars, for this, there is no problem. There is an interesting study here about, again, the lambda CDM simulation, that they also fit the RAR and the mass discrepancy relation, which is also what the MOND predict also. And the interesting thing is that you see this MDAR here with the color is the mass of the galaxy, so it depends a lot on mass. The RAR is here. But what is interesting is that, of course, in the simulation, you can go to Z equal 3 and know if this A naught that they find also in the RAR is at a critical acceleration, depends on redshift, and that we have no solution for the moment. But at least in the simulation, they show that it is 3 times less at Z equals 3. So I don't know if it is lambda CDM or MOND that you believe, but at least we should predict that it will be less Mond effect at high redshift. Okay, now I just go to the second part, the second solution out of CDM. It's a fuzzy dark matter. So fuzzy dark matter, you have already heard about it. What is it? It is inspired by particle physics where you have the action of the particle invented for the CP vibration, but this particle was more massive. It was not lower than micro electron volt. Here, as you see, it is 10 to the minus 22. So it's not really an action. What we call it is an ALP, action-like particle. It's not an action, it's an action-like. So why do we choose this de Broglie length here? It's quantum mechanics. So you have de Broglie, which is h, physical constant of quantum mechanics, over mv, the mass of the action and the velocity. And what we want to solve already intrinsically is that the core cause problem, you have a core. If this particle is different than the neutralino and the WIMP, because the WIMP is a fermion, here you have a boson. So this boson can condense by the Bose-Einstein condensate in the center. It makes a soliton. And if you want that the soliton size is 1 kiloparsec, because when you have a dwarf, you have a core which is 1 kiloparsec, and it is a laboratory for dark matter. So you want that this is 1 kiloparsec or so, and then it is exactly this mass which is implied by this. You have another advantage, is that because of the quantum pressure, you suppress the small, it's like a WDM or a warm dark matter. You suppress the structures below a cut, which is 3 × 10⁸, and in function of the mass. So you solve the missing satellite problems in the CDM. So at least you have two solutions in one. Well, it is also a long history. It's like Mond. It's 40 years ago that it has been proposed by Baldecchi, Ruffini. They proposed both a fermion and boson, but we retain only this one. And recently, because supersymmetry was not found and neutralino was a problem, maybe, this has been a lot studied more. And you have a review here, you et al., very good here, to know what are the advantages and problems of this option. Okay. Now, in this kind of FDM, you have the early universe is completely solved. You see the CDM and isotropies, you see the mass power spectrum and so on. So this is not a problem. The problem is maybe the oscillation, because you have a quantum fluctuations due to the Broglie length. And this is macroscopic, in fact. It has 1 kiloparsec. So you have here some simulation due to shift. For that, they have to solve both the Schrödinger-Poisson equation. So it's a little more lengthy to do this simulation. But you see here that there are two solitons of 1 kiloparsec, two galaxies in interaction. But you have also a lot of oscillation everywhere. And this oscillation will never damp because it's quantum origin. So they will hit, the potential will be fluctuating every time. So if you have a thin disk at the beginning, it will be heated by this fluctuation of the potential, and it can give you a constraint on the mass. So when you look at this, even at every scale here, you have these two 5 kiloparsec, the core, 50 kiloparsec, you have 200 kiloparsec, the filaments. You have big, why you have big de Broglie? Because of course it's over 1 MV. If you have small v, you have also very high fluctuation. So all is fluctuating, and this can put you a constraint on the mass of the action. Okay, so now there is a lot of simulation done in action. You have action gadget, you have also axis à repos, and so on. So it's they are making a lot of modules to take the Schrödinger-Poisson equation. But what the result is, as you can see here, is you make a simulation in CDM. Here is only a zoom of this. You see, if you have good eyes, you see that, of course, you have cut all the small satellites. The main difference is there. And if I pass on to this, you see also that normally the number of satellites in the CDM is there. And in brown is the FDM. Of course, you can cut it in saying, well, all these satellites will not see because they are completely dark, but still, and in mass. And also you see, of course, they have in FDM, you have a core. It was built for that. And in CDM, at least if you have no feedback, you have this cusp. So you see here. And what is interesting, in fact, is that maybe you don't need to evolve your simulation with a very heavy Schrödinger-Poisson equation, because when you make a FDM simulation, it depends only on the initial condition. You see, FDM code to beginning with a CDM initial condition or FDM initial condition is very different, because you have not the small scale structure. While if you evolve in CDM with initial condition and this, you have something which looks like, so you can evolve with CDM code with the initial condition change. It will be about the same. So finally, it's not so heavy. So there are several in literature constraints on the mass of the action. Maybe the most important is this one. So here you have a very dwarf galaxy. Don't look at this, it's a background spiral. But here you have a very ultra-faint dwarf, and in the center you have a star cluster. So if the star cluster is corresponding to the soliton, you should have hitting the star cluster. You should destroy the star cluster, and you have not. So you have put a mass limit of this, which is a little too much. Well, this is discussed in literature. It's not, there may be some resonance and so on. So maybe it's debated. I just mentioned that, but maybe it's too preliminary, because these people jump on the result of James Webb, saying that you have a lot of massive galaxies, and you have, if you have too many small galaxies, you will have too many UV to reionize the universe. So if you shift your mass spectrum towards the high, you could solve this problem. But I think it's preliminary, because you can have a lot of baryonic physics to solve this problem also. So I will go to my conclusion. Here you have two alternatives. The first, in MON, you have some which are success for MON. You have some, as I told at the beginning, some which can be in paths to be solved. And you have big problems to resolve in clusters. And I just mentioned, because it was discussed also a lot, that people think that it's only the bullet cluster that is a problem. In fact, all clusters is a problem. And the bullet is not a special problem, because you have separation of matter and dark matter, because in galaxies, you have always baryons in the center and dark matter at that part. So separation is not a problem, it's the cluster that's a problem. That is, acceleration is not small enough. And for the FDM, of course, there is many constraints. It's not completely definitive. You have the Lyman alpha Flores for the small scale. And well, simulations are quite good. I will mention that nobody has simulated still what the soliton does with a massive black hole in the center, because every galaxy has this massive black hole, so it could interfere. So I think there is a lot of things to work on to find alternatives. So thank you.
Thank you very much. Thank you. We have questions for Françoise. There's one in the front first.
Well, this is more of a comment, just because I see you put that one. So there is actually some sort of works with supermassive black holes treated as point particles. This is actually work that, well, I was involved also at Yale, but there is also people at New Zealand that are working on this.
Okay,
so
okay, interesting.
Yeah,
So I will look.
Hey, when you were comparing simulation runs with CDM and FDM, I was a bit perplexed by the fact that you get an FDM like universe when you run CDM with FDM initial conditions. It does seem like the low the small scale modes of a lambda EDM universe are suppressed. Whether that seems like a contradiction of observations, because we do see some of these small scale structures at lower redshifts. So what's going on here?
Yes. In fact, there are some constraints given by the Lyman alpha for S, for instance, and even for. So it gives well, not in this slide, but it gives a constraint on the mass of the action. So it is a little higher. If it is 10 to the minus 22, it will suppress too much. I given the cut, which was a function of this mass. So if you put 10 to the minus 21 or 10 to the minus 20, it will fit the low small scale structure. So you have constraints.
So we've got time for at least one more question while Florent could please set up. Thank you.
Thanks a lot, Françoise. I have a curiosity. Maybe you've looked at this more and you have a feeling. So in fuzzy dark matter, there's always this solitonic core, and then there is the drop off afterwards. But it seems to me that, how do we reconcile this with the kind of rotation curves that we see, in the sense that you get a core, but this core is much denser?
No, in fact, they fitted to be exactly the rotation curve. So there was not too much transition between, well, at least in the error bars, of course. They fitted to be exactly the core that you observe. In fact, it is not a surprise because it is built to reproduce.
But what happens in this transition regime, I guess, is between the core and the outer part.
Yes, this is not yet completely solved, I think, because there's not enough simulations to answer your question.
Let's thank Françoise again. Our next speaker is a contributed talk by Florent Renaud. He's going to be telling us about probing dark matter or its absence with galaxies.
Thank you. Thank you very much. This talk is going to sound a bit off topic, but stay with me. I promise it's not. So today I'm going to tell you a little story of a personal story, how I ended up there. So I divided it in 3 acts. So without working on dark matter, what am I doing here? First of all, it's a pleasure to be here. It's a pleasure to be in Africa for the first time. This is what I work on. I work on galaxy mergers. You may recognize the antennae galaxies. Maybe you're more familiar with this picture from ALMA, or this one from HST, when you see these fireworks of star formation and star cluster formation. And this is what I work on, and I try to explain how it works. Of course, I'm not the first one. We have a lot of history, especially for the antennae, the closest major merger to us. So these are observations, but already back in 1977, the first simulation showed that you can reproduce the overall morphology with tidal effects and creating these long tidal tails, adding more physics, hydrodynamics, live dark matter halo, and fine-tuning the parameters. We have significantly improved the quality of the model, both for the morphology and the kinematics. Up to the point when we can actually make predictions. We have higher resolution in simulations and in observations now, and we can look at the properties of how stars form, how star clusters, these massive star clusters form and evolved. One of the things that we understood, and trust me, it's going to make sense at some point when I relate that to dark matter, is that when you overlap the potential of 2 galaxies in an interaction, you get zones of tidal compressions, as you see here in red. Here on the right, you see that indeed the mass enclosed in tidal compressive tides is boosted during the time of the pericenter passage. So instead of destroying the matter, as tides usually do, instead they're going to compress it. And if you do that, this means that you have a link between interaction and tidal compression, and therefore you have to change all your equations for equilibrium or fragmentation of things. So if you take the Jeans formalism here, when we have the term of internal pressure and the term of cell gravity, of course, you have to correct for this in the presence of tidal field, whatever the tides are. This is what Chantal did, and she came up with this correction factor here with this lambda parameter, which is the strength of the tidal field. And in compressive tides, lambda is negative. So you see that the Jeans mass is now smaller than what it is without tides. This means that it's easier, basically, to fragment or to collapse structures. So interactions will favor the collapse of structures. And if you do that to gas, of course, at some point you will enhance or you will boost the star formation activity. As you see here on the curve, you have these peaks of the starburst shortly after the pericenter passage. So this is how we explain the starburst activity that we see in interacting galaxies and mergers. We have been testing these theories for quite a while using the antennae, using other galaxies, other configuration. But as a simulator, if I want really to test some ID, I want to go to the parameter file, switch off this parameter and see if I get what is expected. So how do I switch off tides? If I do that, I have to switch off gravity, and therefore I will not get anything. I will not get star formation at all. So then I thought maybe I can not switch off tides, but switch off gravity, but modify gravity. So still, without working on dark matter, let me modify gravity. But of course, I was not the first one to do that. Olivier Thierry and Françoise Combe did several years ago the first Mond simulation of a galaxy merger. So recognize the antennae galaxies and the two tidal tails. So they use sticky particles to treat the hydrodynamics. And basically, the conclusion of this work was to demonstrate for the first time that you can reproduce observed morphology even with the modified Newtonian dynamics. So that was very nice, but they didn't really touch upon the starburst activity or star formation, which was my main interest at the point. So I jumped into this topic, and what I did was to adapt the typical frame workflow that I use. So usually I have stars, gas, and dark matter in my galaxies. I run that with the Ramses code, which treats Newtonian dynamics and hydrodynamics, heating, cooling, star formation, feedback, etc. But for this new experiment, what I did was to just take the stars and the gas, exactly the same, changing nothing else. I leave the dark matter low aside, and then I ran it with the phantom of Ramses code, so a patch of the Ramses code, which deals with modified Newtonian dynamics in a quasi-linear Mons regime, and also the same recipe for hydrodynamics. So very quickly, I have to put some equations on the slides. What we do is just to take the classical Mond framework. When you multiply the Newtonian acceleration by this interpolation function, we use this form and even the normalized version here. So this leads to a modified Poisson equations when your net potential here comes from the baryonic contribution, baryonic density, plus this extra term coming from the Mond formalism. So we do have the Newtonian Poisson's equation on its own, but on top of that, you have this external term, additional term, which is called the phantom density. So it's not matter, but it does the same as some matter to reproduce the Mond effect. So we put all that in the code, we run the simulation, and this is what we get. So in these movies, you see two movies there, and try to synchronize them. You will see in a minute why it's needed, which means that I have to put the lambda CDM simulation on pause now and then. So you will see this pause symbol when I do that. So let's start here with Mond. The galaxies are coming together, CDMs catch up, the galaxy separates. In CDM, they are already back together, they merge, and we have final coalescence. In Mond, it's not at all the case, they are still separating, just falling back on each other right now and merging. So you see the need for the pause button, right? You have very different timescales for these two cases. The reason is that in CDM, we have dynamical friction for dark matter halo, which is large and extended, which leads to rapid coalescence. So typically for galaxy mergers, that's only 100 million years or so, or the order of 100 million years. In Mond, we only have dynamical friction from the baryons, obviously, and not from the dark matter, because there is not. Therefore, we have much, much less orbital angular momentum exchange, and therefore coalescence takes much longer. So if now we look very quickly at the morphology, this is the Newtonian models at the time of the maximum separation between the two galaxies. This is the best model that we have to feed the observations. And if I take these parameters and put them with the Mond solver, this is what I will get at exactly the same scale. So much, much, much larger system. Of course, it's not a fair comparison because I fine-tuned my parameters in the CDM framework, while I apply a different method. So to have a more fair comparison, I did the same fine tuning, but this time in the MOND framework, and I get something which looks much more, which is much more compatible with the observations. And for the sake of completeness, I can take this initial condition and put them in the CDM framework, and this is what I get. So still a smaller system. So now the question is, what happened in terms of star formation for these systems there? It's going to be a bit complicated, but basically what we have here is, as a function of time, the star formation rates for these 4 models. You see, of course, the time scale is very different between the different cases, and different amplitudes for the starburst too. So let me simplify that and have a look only at the 2 models which reproduce morphology and kinematic of the real system, the real observed antenna systems. This is what we have here. And we can, of course, normalize the time to make it easier to compare. So t equals 0 here is the first percenter, t equals 1 is the second percenter passage. And I normalize the star formation rate to the initial value, so the pre-merger value here. You see that in the MOND model, you form many more stars during the first starburst and during the separation of the 2 galaxies than in the Newtonian model. So if I divide one curve by the other, this is what I get, MOND divided by Newton, sorry. I get a peak here with a factor of 3 to 8 times stronger starburst in MOND than in Newton case. So stronger starburst, more spatially extended. But of course, if you burn a lot of gas early on, you don't have a lot of fuel left for the late epochs, and you see that Newton becomes more efficient at triggering a final starburst there. So then there is a side product of all this study that we have also dark matter-free galaxies in these systems. Because if we do look at interacting galaxies and merger, these are observations by Federico, you see here labeled in yellow, you see tidal dwarf galaxies in the tails in a lot of interacting galaxies and systems there. So the process of formation of tidal dwarf galaxies has been reproduced in many, many simulations, including this one from the antennae in lambda CDM. The idea is that you will eject the material from the disks, and with this you can eject marginally stable structure that will collapse in the tails, and or you can also have in situ fragmentation of this subject to form tidal dwarf galaxies. This means that because it's coming from the disk, there is little to no dark matter in these galaxies. So if you put them in a Tully-Fisher diagram, they stand apart, right? They don't have the same behavior, the same missing mass behavior than for normal galaxies, which support the idea of dark matter as opposed to modified gravity. But here we have to be a bit careful because we are not sure the tidal dwarf galaxy is an equilibrium, and we can actually rely on the measurements of the Tully-Fisher diagram. And we don't know also the effect of the merger remnant, which is very massive objects nearby. So external field effect in MOND, normal classical tides in CDM. So maybe the tidal dwarf galaxies the properties are too uncertain to be used as a constraint of the 2 frameworks. But maybe there is a much simpler way to deal with that. If again, I look at these movies, I see that there is no dark matter in the tidal tails in CDM, therefore very, very few tidal dwarf galaxies with little off-galactic star formation. But in MOND, you see all these little knots, these beads on the string along these tidal tails, because every single overdensity creates its own phantom dark matter, so its own potential well that helps the fragmentation and that helps to form more off-galactic star formation activity. So what are the observations telling us? Well, we have very few tidal dwarf galaxies in observations, only 1, 2, or 3, which seems to be compatible with what we have in CDM simulations. Near the tip of the tidal tails, you have 1 or 2 tidal dwarf galaxies at high resolution simulations. By the way, this is where the tidal field is compressive, so another point for that. But this is very sensitive to numerical resolution, and we have to be careful of that. If you do a different simulation with a lower resolution, you will see many more knots because of numerical fragmentation there. So maybe this is not a very conclusive argument for that. So do we have too many tidal dwarf galaxies in MOND? Well, maybe, but we have to be very careful with the numerics for that. Time for me to conclude. We have the absence of dark matter, which means weak dynamical friction and longer dynamical timescale. The connection between starbursts and compression works. That's very nice to see. The starbursts are stronger and more especially extended in Mond, and we can use tidal dwarf galaxies properties as observational test of gravity, but it's tricky. Instead, maybe because of the self-phantom dark matter in tidal tails favor of fragmentation and the formation of many tidal dwarf galaxies, we could instead use a number of tidal dwarf galaxies as observational test of the gravity. Maybe that's the way to go. And yeah, I still don't work on dark matter. Thank you.
Thank you very much. Do we have questions?
Thanks, Flora. Aside from the number of these tidal dwarfs, are there maybe some other property, sizes, or something else that can be used to differentiate between the two?
So this is a very interesting point and a very tricky one, because if you want to use some sort of these properties, you need to know better the survival of tidal dwarf galaxies, how long they survive, what kind of tidal field will stretch them or will dissolve them, etc. And this, whatever the framework, CDM or Mond, it's very difficult to constrain. So I guess we need better and more simulations, so more systems, different configurations, and to look at the timescale for survival. But that's tough.
Hi. You partially answered my question, but so I'm just going to make a comment on what was just said and say there are simulations where either the dark matter or the baryonic component of these galaxies is removed, and we see some very different properties of the central potential of both immersion galaxies and the tidal components. So particularly at the center of the potential. So I'm wondering if there is if you see anything in the Mond simulations that suggests a very different mass profile.
In the tidal dwarf or in general? Either, okay. I haven't looked at that in details because I don't work on dark matter. That's probably that's a very good idea. Actually, we could have a look at maybe not only the central but also the outskirts, which are more sensitive to the tidal effects, and see if we can learn something about that, and then look at merger remnants in observations. Maybe that's a good idea. Thank you.
Okay, that's all the time we had for questions. Let's thank the speaker again, please. Please do put your questions on Slack, and if you've given a talk, please have a look on Slack for questions as well. So our next speaker is also a contributed talk, John McKean, who will be telling us about testing models for dark matter with extremely high angular resolution imaging of gravitational lenses. Can we please have the slides?
Oh, yeah. Yeah, the big green arrow. So hi, everybody. Yes, my name is John McKean. I'm a DSI NRF National Facilities Research Chair here in South Africa, focusing on very long baseline interferometry or high angular resolution astronomy. I'm also a faculty member at the University of Groningen. And the work I'm presenting today is really from a large collaboration of people. I'm just highlighting a few of the main contributors: Simona Vegetti and Devon Powell at MPA, Christiana Spingala, who's in the audience, Hannah Stacey, ISO, and Willem de Roo, who's a student working with me. There's also quite a few other people involved in this. So yeah, the goal of this, of course, is to test the different models for dark matter. We've seen these plots several times. But the key idea is we want to try and differentiate between what is a cold dark matter and a warm dark matter universe. The key observable being that there's a difference in the abundance of subhalos within these two models, and also there's differences in the properties of those subhalos, in that the cold dark matter are more concentrated. So we can use the concentration and also the mass function of subhalos to try and discriminate between these models. And as we've heard of several times today, there's also another option, which is fuzzy dark matter, wave-like dark matter models, which also we can try and test. And what's interesting about these models is that on the large scale, cluster scales, down to even galaxy scales, they're actually quite similar. It's only when you go to the small scales that we really see those differences. So we try and test that using gravitational lensing. So for those of you that don't know about gravitational lensing, here's an example. This is a kangaroo. And if you gravitationally lens a kangaroo, you'll get multiple images of the kangaroo. And the shape, the resulting surface brightness distribution that we observe, the lens surface brightness distribution, tells a lot about the mass properties of the galaxy. So for example, the separation between the different images of the kangaroo tells us something about the enclosed mass. The shape that we see, this looks rather circular, but if this is elongated, it tells us something about the ellipticity of the halo. And also, if we look at the relative sizes of these images that they're produced, that can also tell us something about the radial mass profile, okay? Now, that's looking at the large-scale structure of the halo, but what we really care about is small-scale structure. So if I was to put a small halo, very close, a subhalo, very close to the arc, which is perhaps part of the main halo, then that small part of the arc will be deformed in some way. And the fact that we don't see the same deformation in the other image allows us to make this discovery, okay, that there's a subhalo. I think Leon Koopman's in the audience, and I think he referred to this as redundant information that we have from the different lensed images. What you may also notice is that in some cases you can get multiple images that are even caused by the small satellite, and that tells us something about the concentration of the satellite galaxy. Okay, so in order to do this type of work, there's have to be in a development of a rather sophisticated lens code. We're using a fully Bayesian forward modeling in the visibility plane, where we would solve for some kind of source surface brightness distribution. We then lens it like we did with the kangaroo. We then sample that using our UV plane and add noise, and then we can compare with the data. Okay, so this is the process we use. This is a fully forward modeling technique. It's mainly been developed by Devon Powell at MPA, applying it to visibility data. But this is work that started about 20 years ago with Simon Dye and Stephen Warren in London, Leon Koopmans and Simona Vigetti in Groningen, and also Sherry Sehu and Roger Blanford in California. But we've been really focusing on how this operates at radio wavelengths, and we've developed a number of codes, or we've developed this code over the last sort of 10 years or so. We were the first to sort of demonstrate a pixelated mass and source model for reconstructing the background object. There's a really nice result, which I'm also showing the figure of here from Francesca Rizzo, where there's a simultaneous mass of the lens and kinematic source model that can be fitted with the code. Recently, we've just put on the archive a joint lens modeling and the lens magnetic field analysis. And in the future, in the very near future, we'll be adding scattering to the code as well. But yeah, our main goal is to try and understand what are the properties of the different halos. So I'm going to be presenting a number of data sets. And as the title suggested, it's extremely high angular resolution data we're using. And we're starting off in the low resolution regime, which is using ALMA. And this is what ALMA looks like. These are the lenses that we've been using. These are about 30 to 25 to about 50 milliarc seconds angular resolution. So this is very detailed data that came from ALMA. This is SDPD1, the South Pole Telescope SPT 0532 minus 50, and then we have SPT 053 at minus 50. Source redshifts are very high. Lens redshifts are a bit on the low side. So these ones are low and this one is high. And we'll come back to that a little bit later. So we've done an analysis of what the mass distributions are of the galaxies on large scales. This is the data that we have. This is our residuals that we get after fitting, and then this is the resulting source model. And I just wanted to highlight one thing, and that is we do make very good and accurate source models now. The lensing codes and the data are incredibly sophisticated, so that how good is the lens model is a question you often get from a time allocation committee when people try and do high redshift work. But these are incredibly sophisticated now, and we have very detailed background sources. So we fit an elliptical power law plus shear typically, where our free parameters are really just the impact parameter, the slope of the mass distribution, and this is a function of radius. And what we find is that this on its own is not a very good fit to the data. and we have to add additional mass complexity. And I think we had Sam talking about this earlier with the JWST. So this is the additional mass complexity that we have to add in this so-called multipole expansion, which looks very odd and very unphysical. But the key thing is that what we're doing is we're essentially changing the potential in the regions where we have information, which is the lensed images. And what we find is that there are base factors of order of 28 to about 120 higher when we had this mass complexity than we just have a power law model on its own. Okay, so the nature of this focus meeting is luminous and dark matter. So what happens when we actually look at what the luminous structure of these galaxies are? This is from HST, and this is all work done by Hannah Stacey, and it's on the archive. And what Hannah did is she looked at the surface brightness distributor profiles of these different lens galaxies and compared them with the resulting mass structure that we see. So that the thick colors in red-ish is what the mass distribution looks like. And then the sort of grayish contours is what the optical distribution is like. And we see there's actually quite a good similarity for these two lenses, whereas the one in the middle, there's quite a significant difference. The reason for that is not quite clear at the moment, but we do notice that these are the low redshift cases and this is the high redshift case. So it might well be an environmental effect. Okay. So we'd like to do this for more lenses in the future. We only have a few. I think this is some data I obtained from ALMA in the last cycle. This is for 10 lenses that were observed that we'll be able to carry out this analysis for to determine where or not the light and the mass that we're seeing are really tracing each other or if there's significant differences. Okay, but we want to go to higher angular resolution in order to understand the properties of the subhalos. And for that, we have to go to centimeter wavelengths, where we combine radio telescopes from around the world. And primarily, we're using the one in blue, which is the European VLBI network, which includes our national facility here in South Africa, as well as the telescopes in America, the Very Long Baseline Array. So this is a global VLBI array, and this is the data that I'll be showing you. And this allows us to obtain milli-arc-second scale angular resolution. And this is the type of data quality you can get with a VLBI array, looking at a rather bright gravitational lens. You have this really wonderful sharp arcs and multiple images that we see. And the work done by Christiana in 2019, she demonstrated that it was very, very difficult to try and fit this with a smooth model. Already at this stage, we could tell there was milli-arc-second offsets in the various images. We couldn't fit them with any level of precision. And now, using our more sophisticated lens code, we're able to fit for the lens, for the lens mass distribution. Oh, sorry, here. And that gives us a source distribution from which we get the lens distribution. And now what we find is the mass complexity that we have to have for this particular system now has a base factor of about 15,000, which is ridiculously high. Okay, so before we were seeing cases of a few tens from the base factor for mass complexity. Now we're seeing things in the tens of thousands. And that's because of the extremely high quality of the data that we have, extremely high angular resolution. So we're really looking at the mass properties on very small scales. And what we're finding is about 2.5% of the halo has to be in this extra structure. Okay. And one of the things that Devin did was to also use this data, not just looking at the large scale properties, but we could test fuzzy dark matter models. And so this is just an example of some of the analysis. So this is various types of halo that we try and fit the data with. And this is an extremely fuzzy system. And you can see it becomes less and less fuzzy as you go towards the right. And what we find is that it's impossible to focus the source. It's impossible to get the object to focus on the same spot. So we're using that as a way of checking things. So basically, if this is what our best fitting model is, and here you can see a very focused source which we can use to test the fuzzy dark matter models. This is the constraint that we got. This is our 20:1. I forgot what it is now, something ratio. And this is for various different other techniques, other gravitational lensing methods, as well as the satellites. But you can see our constraint as well off what you can do with dwarf galaxies, where the low velocity of those galaxies, it means that the objects are more sensitive to this. Okay, so what I wanted to focus on at the end is this detection of a 10⁶ mass concentration that we found from another system. So this is a beautiful, a really nice gravitational arc, very, very thin. And what we find is if you focus in this region here and we observe at a little bit higher angular resolution, we see a gap. Just like in the case of the kangaroo I showed you at the beginning, part of the arc has been deformed. If we try and fit this, so this is without the subhalo, you get a nice smooth structure. We have an image residual at the location of our mass concentration. And if we include the subhalo, then we can see we have a nice low residual there. The take-home message at the moment is that we almost certainly have a 10 to the 6 mass structure, which is affecting the lensed images. It's highly preferred relative to a smooth model with a base factor of about 350. And we're currently testing the various other models for what this could be. At the moment, we're looking at a truncated isothermal profile, but we've also tested the black hole globular cluster, and we're testing the NFW right now. And what we're finding, though, is that it's extremely compact. That's one of the main take-home messages we've got at the moment. In terms of the abundance, this would be a very interesting detection. We would expect, if we don't see any more of these halos and 3 more lenses, this would be a problem for CDM in terms of abundance. It depends very much on the mass fraction, but the fact that we're seeing this is a bit problematic for warm dark matter models. Okay, but we'd like to find more lenses, and I'll talk about that in another talk in the future because I'm out of time. But in principle, we can do this with next generation radio interferometers. And I'll finish up with my summary here, which you can all read. It's quite a short talk. But I did want to highlight that if you're excited by this research and would like to get involved, we have a number of postdoc positions available, and just come and talk to me about it. Okay, thank you.
All hands came up at once. I'll go for people who haven't yet had a chance to ask.
Thank you. So I maybe we didn't get it, but how are your substructures in the mass, let's say, related to possible substructures that you see in the luminous distribution of the lens?
How are they related?
Yes.
Okay, so we don't know where these halos are to some extent. We know they're somewhere along the line of sight. If they're not within the dark matter halo, then that means our line of sight effect. We expect to see those. That's a test of dark matter also. It's actually technically a cleaner test of dark matter because they shouldn't be truncated by the interactions within the galaxy. So when we look at our numbers that we expect, it's how many we expect in the halo and how many along the line of sight. So I don't know if that answers your question. Okay. So,
very quick question. Quick one?
I hope so. So I didn't quite understand your last point. I think you said there was not enough of these objects for CDM, these blips, but too many for WDM. Is there like a Goldilocks zone here?
Yeah. So maybe sorry, was this on my summary? Maybe I misput it. Sorry. So I think it should be that they're.
So something in between works?
Well, yeah. Well, I don't know. I mean, I think that's what we're now going to test is like what kind of model would best present this. The issue is that I think the abundance of them, the fact that we're seeing them is a problem for warm dark matter, and the fact that they're so concentrated might be an issue for cold dark matter.
Well, that's all the time we have for questions, but please put your questions on Slack if you have them. And again, I remind the speakers to have a look on Slack. So let's thank John again. Our next speaker is Jiani Chu. I believe this is where we hear the second half of the story we heard earlier. So I'm looking forward to that. The title is Galaxy Stellar and Total Mass Estimation Using Machine Learning. Can we please have the slides? And yeah, welcome, Jiani.
Good afternoon, everyone. I'm Jian Chu from Tsinghua University. Today, I'm very happy to be here to share our recent work, measure gas mass using machine learning. I work with Professor Dan Xu in Tsinghua, and I also collaborate with Hongming-Tang, Shen Donglu, and Richard Long in this project. Gas formation and gas evolution is an important topic in astronomy field, and to study gas evolution, to have a good measurement of gas physical property is important. And one important property is luminous and dark matter composition. In this study, we investigate gas masses and mass ratio and dark matter fraction. And in observation, we have gas images, and sometimes we have spectroscopy. How we get a gassy physical property from observation? I believe we have learned many methods in this focus meeting. And one method is stellar population synthesis, which can tell us the gassy mass from multi-band photometries. And another is strong gravitational lensing, which can give accurate total mass estimation. And we have dynamical modeling methods such as STRAM and Schwarz modeling method. These two methods both take gassy images and velocity maps as input, and gassy velocity maps can be derived from IFU data. And there are already many IFU surveys such as S3D, SEMI, Manga, KMOS, and so on. But conventional dynamical modeling method may have model assumptions and model degeneracies, which may cause bias and systematics. Here, we want to ask a more fundamental question: whether current observations provide sufficient information to decode true dynamical property of external gases. To answer this question, we go for machine learning, because machine learning uses a large number of parameters to mimic any model, thus avoids explicit model assumptions. And machine learning also have grown fast in the past decade. This figure shows the cross linkage between the astronomy research and the different technical methods as a function of time. This linkage is derived from large language model, and the larger the value is, means this technical method is more well adopted in astronomy research. And we can find that in the past decades, machine learning has been integrated to astronomy research very rapidly. One machine learning method we use is the convolutional neural network. The neural network can be understood as a complex function that takes input, returns output. There are many parameters in hidden layers, thus neural network will be very powerful. And CNN is named by the convolutional layer it contains, which can extract image feature and reduce computational complexity. Thus, neural network CNN is very suitable for image processing. The specific network we use is ResNet 18, which is the winner of ImageNet large-scale facial recognition challenge in 2015. And another method we use is GBDT, gradient boosting decision tree. GBDT uses a series of decision trees to give the final prediction. It's suitable for cat-log data processing, and it can give us feature importance after training, which can tell us what inputs contribute to the prediction. In practice, we use LightGBM, a GPT package developed by Microsoft, which takes much less time in training compared to the original algorithm. Yes, we use GPT to understand why CNN could work. What's the key feature? And both these two machine learning methods are supervised machine learning, which means we need a data set with good measurement of mass. So we go for simulation. And Illustrious TNG is a suite of state-of-art cosmological simulations. We selected 9,000 gases from TNG 100 and projected these gases along simulation box axis XYZ. So in total, we will have a sample with 28,000 gases. Here is our workflow. Firstly, we generated manga-like gassy samples from TNG 100. There are galaxy R-band image, galaxy color map, mean velocity map, and velocity dispersion map. And then we use multi-band convolutional neural network to predict the gassy total mass, stellar mass, matter ratio, and dark matter fraction separately. As we mentioned before, convolutional neural network is very suitable for image processing. And to further understand why CNN could work, what global property contributes to the prediction, we derive summary statistics from these input images and maps. Their gassy magnitude, velocity dispersion, color, and so on. And then we use GPT to predict the same property. And by analyzing feature importance, we will know what feature contributes to the prediction. Now let's see our machine learning results. How good measurement machine learning can give compared to the conventional dynamical modeling method. Firstly, we show total mass prediction. In the left, in the left figure, we show the CNN prediction on test set. The x-axis is the true value, and the y-axis is the predict value. And the scatter, the relative error is about 0.06x. And in the right figure, we show the GPT results, and the relative error is about 0.08 dex. A little larger, but makes sense because summary statistics lose spatial information. And as Borcho said, gassy morphology encode gassy information. In observation, we can get the gassy total mass from stellar kinematics or gravitational lensing. So here we list a conventional dynamical modeling method, GEM results on illustrious gassy reported in Li Hong's work. And we can find that machine learning can give machine learning prediction is similar to GEM, but machine learning performs much better in stellar mass prediction. From in the left figure, we can find that the relative error about CNN is about 0.04 dex with gassy R1 image and mean velocity and velocity temperature as input. And in the right figure, we can see the GPT, the uncertainty of GPT is about 0.05 dex. And by analyzing feature importance, we can find that for both these two mass prediction, gassy luminosity as a dominant feature, same velocity dispersion. The connection between the total mass and the galaxy luminosity may indicate that there are certain fundamental plans of these galaxies. And the tighter connection between the stellar mass and the galaxy luminosity may be a consequence of direct conversion of stellar to mass ratio. And machine learning do perform better in stellar to mass ratio prediction. We can find that from feature importance, velocity dispersion map and gassy color are important to the mass ratio prediction. So we included the color map in CNN, and then the relative error of mass ratio prediction will be about 0.04 dex. At last, we show dark matter fraction result. In CNN, we did not use CNN to predict dark matter fraction directly. Instead, we use CNN to predict stellar mass and total mass simultaneously, and then use these two predictions to infer dark matter fraction. And we can find that the relative error is about 0.05 dex. And that is systematic because the inferred dark matter fraction is actually the dark matter fraction plus gas fraction. And then use in the right, the GPT results, we can find that from feature importance, velocity dispersion and the stellar spin are important. The connection between the stellar spin and the dark matter fraction indicates that for gassy stellar and dark matter components, their properties, their evolutionary history are entangled. And together with the connection between the velocity dispersion and the mass ratio, it tells us that there are different mechanism shapes the property of stellar and the dark matter components. And to now, we only use machine learning to predict gassy property at one aperture. What about the density profile? Here is the preliminary results on gassy total density profile prediction. This scatter plot shows the local density prediction versus ground truth in 20 beings within 3 effect radius. And the average uncertainty is about 0.13 dex. We are still working on it. It's very preliminary results. And we have more details in this published paper and all main secrets in this GitHub page. And so going back to the questions we asked before, whether current observations provide sufficient information to decode true dynamical properties of external gases. In our work, we use machine learning, which avoids explicit model assumptions. And machine learning do successfully reproduce gassy aperture property from multi-band images and stellar kinematics. And for mass prediction, gas luminosity and velocity dispersion are important. And for mass ratio, color or star formation rate can help to predict. And for dark matter fraction, stellar spin is important to the prediction. And so I think you all have the answer to this question. And the answer is yes. Thank you.
Fantastic. Do we have a question for Jenny?
Thank you, Jenny, for this interesting talk. So what's your next plan to understand the better? Because I have many doubts, which I will just say very briefly. So simulations do not behave very well just to reproduce the observed universe. So there is problem in estimating the main sequence of galaxy, which is star formation rate versus stellar mass of galaxies, which varies, for example, in TNG simulation at different redshift, and we don't know what's happening there. And also cold dark matter, we don't know. So how you will tune your machine learning model in order to predict something realistic, seeing the uncertainties, biases, unobserved features in these simulations?
There are certain machine learning techniques can handle this problem. If the simulation have a certain domain and the observed galaxy have a certain domain, and the domain adaptation method can kind of solve this problem. As far as I know, there are a group use CN and to predict active fraction, and they successfully use the machine learning method trained on TNG and can predict well in ego data. And they use Mangia. This method trained on Mangia can reproduce. Sorry, it's trained on Mangia and they use this method to observational data.
Galaxies, or you pick up galaxies from all across, like up to some certain redshift when you trained your model? Did you pick only local galaxies?
Yeah. To now only redshift 0.
So if you apply your model, if your model is really accurate, if you apply your model at redshift 1, what do you expect there? Are you obtaining accurate dark matter fraction there, or stellar properties, star formation properties? Did you try that, or will you try that in future?
I have not used domain adaptation yet, but it's not reasonable to use the machine learning trained on TNG and directly use it on observation. There are many steps to go.
Is there?
So there are quite a number of assumptions to make the mock observations, like the manga mock here. And so what is your, like, how do you estimate the influence of all these assumptions, in the sense that they're like, you assume things related to maybe radiative transfer or whatever. And so how does this influence the results eventually?
As the mock data is very simple. We just assign the smooth particle on the mesh and do dust attenuation, a single formula dust attenuation, and don't do radio transfer. It's the mock data yet is not such realistic yet. And for the assumption you mentioned, we have not explored the CR effect.
Well, I think if there are more questions, please put them on the Slack. But let's thank Gianni again for a great talk. Thank you. So our next speaker is a pre-recorded. The speaker is going to be online to answer questions after the talk. So the next speaker is Connor Stone, and the video will be about caustics, a differentiable GPU-accelerated gravitational lensing simulator. It's like Interstellar.
Sounds like it's being corrupted. Maybe I should just do the presentation virtually. Perhaps I can just give the presentation virtually.
Apologies, Connor. It's coming out really strange from our end.
Can you hear me?
Oh yeah, would you rather just give the talk? Because that seems to work.
I'll just give the talk virtually.
Okay,
then.
thank you.
All right, let me share my screen. I'm I don't know why that didn't work, but oh, I guess I gotta go right back to the beginning. Okay. Can you see my screen and me?
Yep.
Okay. So yeah, hello everyone. I'm going to talk to you about caustics. My name is Connor Stone. I'm a postdoctoral fellow at the University of Montreal in Canada. I would love to be joining you in person, but my 9-month-old baby at home says otherwise. So, caustics. Before I get into the gravitational lensing simulator, I'm just going to do a quick background on gravitational lensing. People have already discussed it in this session, but the basic idea is that if two objects align on the sky, the mass of the intervening object is going to deflect the light coming from the background source. So you get to see multiple distorted versions of that background source, but they're magnified and warped in ways that we can take advantage of to do all sorts of really cool science. But one that I find really interesting is, as discussed before, the gravitational lensing is sensitive to all the mass that it encounters on its path, which means that tiny deflections from subhalos are entirely possible to detect. And these would be sensitive to the differences between cold dark matter and warm dark matter. It's been shown in other literature that really we should be competitively sensitive to the differences between cold dark matter and warm dark matter using gravitational lensing, but the calculations are really complicated. We've already seen some high resolution gravitational lenses. I work mostly in the optical. So a lens like this is kind of what I think of looking at, and we're looking for extremely subtle perturbations in these images caused by the subhalos, something of order like pixel scale transformations. So we want to be really, really sure about our analysis. We want to be doing a really robust and principled Bayesian inference that tells us what our uncertainty is if we do get a measurement. Now, I'll get back to how we actually want to carry that out. But first, here's another assortment of gravitational lenses. There's of order thousands that we know of right now in various configurations. And it takes a lot of computing power to process any of these images. Think of order like a week of compute in order to get some really robust results that explore a parameter space. But coming soon, we're going to get orders of magnitude more gravitational lenses to look at. Surveys like Euclid and Rubin are really going to expand this by a huge amount. So we need to do processing faster and in more detail in order to get all of the science out of these gravitational lenses. Enter caustics, the code that we've been working on to analyze gravitational lenses. It does all of the analytics of gravitational lensing, ray propagation, and various other calculations that are involved, but it's written entirely in PyTorch using the, it's written entirely in Python using the PyTorch package. And that gives us access to 2 killer apps. One of them is GPU acceleration for all of our calculations, and the other one is automatic differentiation. So I'm going to get into how caustics takes advantage of these features. First, the GPU acceleration. So here I'm showing runtime for generating images like you see on the side here versus the number of images that I'm generating in one go. And the blue and orange lines, those are using a single CPU, either using Lenstronomy, which is like a widely used gravitational lensing code, state of the art, or orange is caustics, our code, which performs about the same on a single CPU, as you'd expect, because they're utilizing the same resources. But if we go to a GPU, that's the purple line, more than 2 orders of magnitude speed up in terms of generating large amounts of these images. So you could envision running 100 MCMC chains simultaneously. You would be maximally taking advantage of the GPU and getting orders of magnitude speed up in your calculations. So this is how we can meet the upcoming huge amount of data that's coming. But we also need to be doing more sophisticated analysis. So to do that, we're going to be using automatic differentiation, which basically all of the calculations that we do in our gravitational lensing code are tracked by PyTorch, and then we can go backwards through those calculations and use the chain rule to propagate derivatives wherever we want. So you can imagine for an image like this, if I wanted to know for every pixel, what is the derivative of the brightness of that pixel with respect to every parameter, that's what you're looking at down at the bottom here. So this is the essentially Jacobian of that image, where we know what the derivative of the brightness is for every parameter. It gives us a huge amount of information and lets us take advantage of some really sophisticated algorithms. So these are generally called score-based models. The basic idea is you take Bayes' theorem, and you take the log of the Bayes' theorem, and then you take the derivative with respect to your parameters that you're trying to model. And that gives you an alternative version of Bayes' theorem, which is entirely valid. You can do MCMC algorithms on it, like Hamiltonian Monte Carlo, that can very efficiently sample a large parameter space. But we're going to use a different kind of score-based model called a diffusion model. So what this allows us to do is take the likelihood term of Bayes' theorem and entirely model that analytically. We do gravitational lensing exactly using gravitational lensing equations. We can compute a chi-squared and get derivatives through all of that using caustics. So we get a likelihood that drives us towards whatever data we're observing very, very accurately. But then because gravitational lensing is an ill-posed inverse problem, where technically you can't just invert the result, you get something that makes no sense when you do that. You need a prior on what galaxies should look like. And that we can use a machine learning model that has just looked at a large number of unlensed galaxies and has learned what galaxies should look like. The really powerful thing that you can do with this is posterior sampling of the sources that could have explained a given image. So here I'm looking at a galaxy that we have gravitationally lensed, added some noise on, and created some mock data to look at. Then using this posterior sampling diffusion procedure, we can actually recover what that background galaxy would have looked like using our prior that galaxies should look like galaxies and our likelihood from caustics that does all of the gravitational lensing calculations and likelihood for us. This is pretty wild. I mean, I was blown away when I saw this, but actually this result is getting old. It's almost 2 years old now by Alex in our group here in Montreal. And we've been trying to push further and further on this. So one thing that we want to do is make sure that we're doing our statistics right. And so in the group, there's been tests developed that allow us to show that we're not just sampling some images that look really good, but actually doing true posterior sampling in a real Bayesian analysis that we can say that we can say that our sample of images actually covers a posterior distribution. When we say the true value should be within this range 40% of the time, we really mean 40% of the time. I'm not going to get into the detail of how TARP works, but it's a really cool algorithm that you can use generally to test posterior sampling for any Bayesian procedure. Next, we've been looking at the prior, because the prior, of course, is going to be wrong. We're going to train it on galaxies that are likely nearby, high resolution, but then apply it at high redshift galaxies in gravitational lensing scenarios. So Misa in the group, he tried analyzing a gravitational lens where here's the galaxy, and then we gravitationally lens it, and then he does posterior sampling using an incorrect prior that's only ever seen elliptical galaxies, or the correct prior that does know about spiral galaxies. Of course, if you use the wrong prior, you are biased and you get incorrect results. So he developed a procedure, an iterative procedure that uses gravitational lensing data, because we're going to have tons of it, uses gravitational lensing data and actually iteratively improves the posterior samples by taking those posterior samples and training on them and trying to learn from them. And so the top row is the data that he had to work with. The second row is his first round of posterior sampling where all his model knew about was elliptical galaxies, and those, of course, look like elliptical galaxies. The third row is after iteratively learning from this data, and then the final row is what the true values should have been. And you can see that he's actually converged very well towards what the true prior should have been, so that he's creating less biased samples. This is really, really neat that we can do this.
Sorry to interrupt, 2 minutes.
Okay, yeah. Sasha in our group has been taking this diffusion model procedure and trying to apply it to star formation history recovering. So we can actually analyze the history of these gravitationally lensed galaxies when we start to analyze them in more detail. And she can actually draw a posterior distribution of star formation histories to explain the history of a galaxy. Really, really cool. So yeah, Caustics is going to let us do some really powerful analysis of gravitational lenses. We're really excited for what it can do. We've created tons of documentation for the code, and you can just do pip install Caustics and you can get going. One thing I should mention is on our website, we've got tons of tutorial notebooks that explain how everything works. We've also got a graphical interface where you can play around with gravitational lensing and even play around with a picture of yourself and create a new profile picture for yourself if you want. So that's really fun. Check out our website for that. Before I finish off, I'll just mention all these cool PyTorch advantages have also been encoded into a package called AstroPhoto, which lets you do photometry in a really Pythonic way. You build models as objects of an image. You can do multi-band imaging. You can do simultaneous object and PSF recovery. It's really powerful. I suggest you take it out I suggest you check it out if you're doing any photometry. So yeah, thank you for listening.
Fantastic. Do we have any questions for Connor? Everybody's a bit stumped. I did have a question though. So I would like to know, in terms of the input, the prior, you mentioned briefly that depending on the galaxy that you give it to train, it may not get the right answer. What do you do about those background galaxies that we may not yet have the same band, for example, a sample of galaxies in the same band? Galaxies look different depending on the wavelength. We may not have a big enough sample to properly get those. Have you got a plan for how to get a proper prior for things that are maybe at higher redshift?
Right. So the thinking right now is that we would actually use the gravitational lensing data to infer better priors by doing the posterior sampling with whatever prior we have, that those posteriors are informed by the prior we had, which may be wrong, and the likelihood, all of the data that's come in from the telescope. And as you iteratively do this procedure more often, you get to like soak up that information from all of these telescope observations. And even though what you're looking at is lensed and warped and everything, you actually converge towards better prior. I should also mention that this is a Bayesian procedure. So if you have high quality data, you get high quality results, even if your prior was wrong, because the prior gets overpowered by the likelihood. Here we took a number 7, which is not a galaxy at all. It doesn't look like a galaxy. But when you have high quality data, the posterior samples recover that 7 really well because the likelihood overpowers the prior. It doesn't matter that you had the wrong prior. It's only a challenge when you have worse and worse data. But actually, there's a huge amount of data in an image. And when you're doing a pixel level analysis, you get to take advantage of all of that. So we think we have some really powerful tools to deal with a prior which may be slightly misspecified to begin with.
Yeah, I love that slide. That's quite impressive. Thank you so much. Let's thank Connor again. So next we've got a short talk. I think the person's online. Anuprit Moore, are you online?
Hi, yes.
Fantastic. Can we show the slides?
Are you able to see the slides?
Yeah, we can now. So go for it.
Okay, thank you. Hi, everyone. I am Anuprita More. I would like to thank the organizers for giving me this opportunity. I'm going to talk about a couple of studies which are aimed towards obtaining statistical constraints on mass distributions from a large sample of strong lenses for galaxies, groups, and clusters. The corresponding references are given at the bottom of the screen. Yeah, so in strong gravitation lensing, we see multiple images of a distant background source. And if we measure the image separation, for a large sample of lenses, then what we can find is that the distribution of these image separations, they depend on the mass distribution of the underlying population of lenses which are in the foreground. In this particular study, we obtained statistical constraints by looking at a large sample of real lenses, and what we found is that this particular the black curve here, which corresponds to a model consisting of a dark matter component and a baryonic component, was able to fit the observations much better. But in order to improve these statistical constraints, we need to work with really much larger sample of lenses, and this is going to be possible very soon thanks to imaging surveys such as the Rubin LSST and Euclid in the near future, where we're going to find thousands and hundreds and thousands of lenses. But in order to achieve our goal, we need algorithms that are fast and efficient for searching lenses, and also we need algorithms that are fast and accurate for predicting the lens model parameters. In this first of its kind study, we did a systematic comparison on the Hyper SupremeCam survey data, which is a precursor to the Rubin LSST. Here we gathered different data sets and neural networks from 4 different teams, and we did several tests and analysis on a common test data set, which consisted of real and mock lenses and also real non-lenses. So in this work, we looked at various metrics, and the results can be found in this paper. Here, I'm just going to talk about one particular result, which shows the true positive rate and the false positive rate, and compares different the 4 different networks, which can be seen here with these colored curves. Each colored curve corresponds to one particular network. The different panels show the different combinations of lenses and non-lenses. These particular panels with the yellow star, they have the combination of the real here the real lenses, all of the real and the real lenses and non-lenses, and here all of the different lens samples and the non-lens samples that were in our test data sets. And overall, what we find is that on these combined samples of lenses and non-lenses, various networks, they perform comparably. But they do, when we are looking at data sets which come from the same team, the networks seem to perform much better on their own data sets, which is visible in some of the other panels. We also exchanged the training data sets, and we found that there were certain networks whose performance improved substantially when we analyzed after interchanging the training data sets. So the takeaway from this particular study is that if you want to have lens search algorithms which are robust and efficient, then we not only we need systematic studies of various neural networks to build to finally come up with a robust algorithm, but we also need to be extremely careful about the nature of objects that are included in these training data sets. In the next study, we constructed a traditional...
Anuprita, I'm sorry to interrupt. I think we're out of time. If you want to wrap up.
Yeah, I just have 1 or 2 more slides. So in this next study, where we looked at a traditional convolutional neural network, where we are predicting the lens model parameters, we found that there are certain parameters like the Einstein radius, which we are able to predict far better compared to some of the other parameters. And this holds true even if we do a comparison only on a handful of confirmed lenses where there are sophisticated modeling results available. And even in these cases, we find that the Einstein radius parameter is predicted far better compared to some of the other parameters. In summary, what I would like to say is that we can obtain statistical constraints on the lens mass distribution using large sample of lenses, but we need to build robust and fast lens search as well as lens modeling parameter prediction algorithms. And there are various challenges with ground-based imaging, which we would like to further tackle with in the next couple of years. Thanks for your attention.
Thank you very much. This concludes the official program. We just wanted to extend a few thanks, so if I may invite.
Okay, so I just wanted to thank everyone for being here, all the speakers for contributing to this focus meeting, which I think was, at least I was very interested by all of the talks. So thank you very much. And I wanted to thank also the technicians who also helped us greatly to have this working. And Samuel Longer to be here for as part of the volunteering team. In fact, most of the SOC was not here in person. And so I think that this was also made possible by all the SOC members. And amongst them, two of them were actually very crucial, and especially Gori, and the other one is Sabine, because they did most of the work to make this workshop happen. And so I think it includes a lot of things to do. So I think that Gori here and Sabine as well online maybe deserve a big thank. Yeah, but not as much. Yes.
So there was a lot of examples for.
Yeah.
You can invite people. Too much in the topic.
I really think, okay, so I have two ideas. I have two ideas about what to do with Control, like some of the diffusion probabilistic model, like in so modeling. Yeah. I'm sure that if you can. I know him really well. Yeah. We co-authored a few papers. Yes.
Well, I'll see you somewhere, sometime.